Welcome to what is a special standalone episode that builds on all the work that I've done in my original, and quite popular actually, DIY PCB Challenge series. Check that out if you haven't seen it. But whereas my original series was more about the development process and sharing my experiences throughout, this video is intended as a full-blown tutorial, and that's why it's so bloody long actually. So in this episode, I will provide an in-depth explanation of how to make high-quality, high-resolution PCBs, all using fairly basic, low-cost equipment, all something that's made possible by following a comprehensive method which I've personally developed. The core concept I started with for this method was to try to do all the primary work using an extremely cheap CNC 3018, with the idea being that you would not only need to deal with less equipment, you also don't need to worry about the issues with geometric matching or scaling, as everything is done in that same coordinate workspace. Now, looking at all the sections in this episode, you might get the impression that this method is difficult or time consuming to achieve, but I can assure you, once you know the steps and have everything you need on hand, it's pretty easy and quick to pump out PCBs. There are also steps such as PCB silkscreen markings which are purely optional, should your design not need it, or you just want to save some time. Anyway, if you carefully follow this method, I'm confident that you will be able to replicate the results that I've been getting, turning a blank piece of copper PCB like this into something that is difficult to differentiate from a manufactured one, and at resolutions where you can use features as small as, say, 0.1mm tracks and 0.2mm square pads, and feature separations as small as 0.12mm. That's all pretty small. Personally, at the time of publishing this episode, I've not actually ever seen anyone present an easily accessible, comprehensive method to make DIY PCBs to the quality of the method that I've developed here. But I've got to admit that I do avoid watching other similar YouTube channels to mine, and I do that in order to keep my originality and obviously motivation to actually make these videos. Even so, in the past I have seen a number of videos with DIY PCBs. Some of them are pretty good actually, but still nothing that's comparable to what I'm doing here on either a cost or a results point of view. Anyway, those who disagree will surely let me know in the comments. Regardless of all that, my hope is that I'm really breaking some new ground here with the method that I've developed, and that in turn will open up doors to many people who have always wanted to make their own high quality DIY PCBs. But if that's actually the case or not, I guess only time will tell. And of course there's always the question of why you would want to make a DIY PCB in the first place, given that it's now cheap and fast just to order a PCB from China. And I've covered this discussion in earlier videos, so just let me touch on it lightly here before I go on, just for those who have missed it. Naturally, there's always a hobby aspect, but there's clearly a practicality to being able to make your own PCBs as well. And assuming you have everything down pat and have everything you need on hand, from preparation of the files in FlatCAM through to the production of a fully populated PCB can actually take as little as 3 hours. And the per PCB cost can also be quite competitive to that you might pay for a PCB from China. Clearly that's dependent on how cheaply you can obtain the raw materials, of course. But now we can start seeing the benefit coming into focus, right? So let me explain a scenario. So for example, you order your PCB from China. This is how it's typically going to go, right? You're going to wait 7 or so days for delivery, only to undoubtedly discover all your mistakes. So what do you do then? Well, you could fix the design and order again. 7 days later it arrives. More mistakes found. Do you fix them? Order again? And the question becomes, well, how many times do you realistically justify repeating this process just for a DIY project? Most people will eventually get to the point pretty quickly where it's just getting too costly or it's taking too long. And that typically means that people are going to use a bodge wire or some other way to just fix the problem and use the board as it is. Ultimately, that's going to obviously result in some degree of disappointment, but you know, that's all you've got, so that's what you do. Now let's contrast that with using this DIY method that I propose. By using this method, in a single day, you could turn out 3 or 4 iterations of the design, ultimately achieving a perfect result, all in a single day's work. Clearly that's going to save you time, get your project moving forward, but it's also going to save you money too, right? Of course, if you then wanted to take your now perfected design and do a large production run, then using the China option then to manufacture them is likely going to make more sense compared to trying to produce tens or hundreds of PCBs with your home rig. So when first going into experimenting to figure out what sort of PCBs I could make with a new DIY jig, I set my bar pretty high. I mean, I always do. That's typically the way I've achieved what I've achieved. I set the bar some stupid level high, and then maybe achieve 90% of it at best, which in the end actually is a pretty good result because I set the bar so high in the first place. I mean, if you get 90% of something which is crazy good, well then it's pretty damn good, right? But honestly, the results that I achieved with developing this method have far exceeded what I ever could have dreamed of when I set out on this journey a couple of years ago. It really has surprised me. And while there have been many supporters in the comments of my earlier videos, there have also been plenty of doubters and naysayers as well, telling me how other people do it different ways, and this way is stupid, and so on and so on. And that's just the way it is, right? The negative comments are actually more of a red flag to a bull, really, for me. I will just keep ramming forward until I achieve what I set out to do. In fact, my whole life has been full of people telling me what's impossible, but I've also had some very generous and fabulous people who have put their faith in me and provided support that made my personal journey possible. So my advice to any youngsters out there listening who are actually trying to achieve something new or different, I would say ignore those naysayers and seek out those rare but special people who might put their faith in you and give you a bit of a foot up and get you on your way. And while I don't see any financial gain from doing all this development work or producing this video, I do ask that you simply give the channel credit in any publication of your work that makes use of part or all of this method. Just include a notice that the method you use is based on the ForOurGood PCB method. Maybe you could even include a link to the video if possible as well. I'll leave that up to you. Now let's quickly touch on the limitations or scope of this tutorial, so to manage expectations a little bit. This method assumes up front that you are competent in using KiCad and you can actually make a PCB design. I'm not teaching that in this lesson. I also only show how to make a very small PCB in this video. It's literally a couple of centimeters by a couple of centimeters. But you can make a PCB as large as the tools and materials you have allow. And for brevity, I only show how to make a single-sided PCB, but all the steps necessary for making double-sided PCBs are actually included. And in the last section of the video, I'll provide some pointers on how you'd go about doing that as well. So what sort of results should you expect by following this method? Well, assuming you are using the exact same stuff that I use and follow the method very carefully, I expect you'll be able to achieve the exact same results that I've been getting. The method has actually been proving to be very reliable to repeat and giving very consistent results. Even so, I expect that you'll need to go through the process of tuning the settings information somewhat, especially when it comes to the laser power and the feed speeds. If your CNC has a little bit more play or is less rigid than mine, then it's likely you're going to need to slow down the feed speed and lower the laser power to get a good result. But while the power and feed settings that I show in this episode may not exactly be plug and play for you, at least you'll have some sort of reference to work with, and that should get you to the final settings you need pretty quickly. You should also be aware that using different makes or colors of UV resins will likely affect the settings that you need to use. This is a pretty sensitive sort of area of the system. But again, once you dial it in, I expect it'll just keep working as it is with whatever you're using, as long as you don't change the resins. So to sum it all up, you're likely still going to need a little bit of experimentation to get your setup working well. This is really no different to what you might face with when you're dealing with 3D printers. But once you get it working, the settings remains pretty stable and you're just going to be able to keep churning out the PCBs. And just before we get into it, a little safety disclaimer. This method uses high power lasers that can blind you. It's dangerous. It creates fumes that can be bad for your health, uses chemicals that can damage your skin or eyes and can generally be bad for your health. Put simply, as with many things that humans often do in life, there's a lot of things used in this method that can be very detrimental to your health if you're not careful. So use your common sense, take the appropriate safety precautions, and wear the appropriate safety gear. And of course, if you're lacking common sense or simply lacking basic life experience, then try to look for an adult who does have that and have them help you out when attempting this method. So anyway, with that all out of the way, let's start getting into it. The key pieces of equipment you need for this method is as follows. You'll need a CNC 3018 or some sort of similar CNC, including a spindle and the necessary clamping hold downs and stuff like that. You'll need a decent power diode laser, preferably something that has an air assist nozzle. You'll need a UV lamp for exposing the UV resin. You'll need a PCB hot plate with some sort of thermal control. You'll also need some sort of watch repair magnifying glasses. They're extremely cheap, so I'm sure you'll find them out there on Amazon or something like that. You'll also need a couple of fine toothbrushes for cleaning, a rubber spatula for laying down the UV resin, laser protection goggles of obviously the correct wavelength for your laser, some sort of fume extraction system, and obviously the normal general eye protection and a fume and a dust mask or something like that as well. As seen in my earlier videos, all these items are relatively inexpensive, but spending a little bit more money may improve the convenience, or in the case of say a higher end CNC 3018, you might actually be able to increase the effective usable resolution as well. If you get the laser with the air assist nozzle, then you're going to need an air compressor and the associated fittings. That's probably going to drive the cost up a bit for most, but even so, I highly recommend to see if you can get it if you can. It's not absolutely necessary, but it really can make a big difference when you're trying to clear those pads, as you'll see a little bit later. A standalone digital microscope is also definitely a nice thing to have, and they're not that expensive. I think mine cost around about $50 and even included an internal battery. You're obviously also going to need the materials for the PCB itself, and that's going to include the blank copper-clad PCBs, the UV resins, the solder paste, and naturally, of course, the necessary components to make your PCB itself. There are quite a few consumables that you'll require as you make these PCBs. You're going to need some good quality, high concentration isopropyl alcohol, IPA as we'll call it from here on, and that's for cleaning. I suggest you buy a big can of it because it's typically a lot cheaper to buy it that way. Nitrile gloves are definitely recommended. The IPA can really do a job on your hands after a while, and you can use them a couple of times before you throw them away, but I just bought a big box of those. You're going to need a lot of tissues for cleaning, and they have to be lotion-free. You don't want any lotion, you just want some dry tissues, but you go through quite a few of those too. Scotch-Brite for cleaning, you'll need that. You'll need some metal polish, such as Pical or Brasso or something equivalent. You're going to need some rags for polishing. You're going to need the silkscreen mesh for leveling the UV resin. We're going to need some ferric chloride for etching, some wide masking tape or some various different sizes of masking tape you're going to need, some CA or super glue for mounting, as well as some accelerator for the super glue as well. And finally, you're going to need various sizes of PCB drills, which I count as consumables because I keep breaking them all the time. Well, not that often anymore, but I do break them on the occasion when I do something stupid. Specifically, you're going to need a 1mm size drill at least, so make sure you have that in your collection. So let's take a quick look at KiCad first, and most importantly I want to show you what layers you need to use and what files you'll need to output to progress to the next stage. I also want to say that I found KiCad to be an amazing piece of software. It's really, really good. So I can definitely highly recommend it, and it's actively being developed and supported, and it's free to all, which is amazingly beneficial to the community. And even though it's free, this is one of those rare situations where I actually think it's an excellent cause to donate to. So if you find that it's of some use to you, and of course you have the means to do so, please consider donating as you see fit. At the time of filming, I am using KiCad version 8. So if you're using an older or a newer version, there may be a few little differences in the UI, but I expect the fundamentals to be much the same in any case, so it should still be a good reference. So let's open it up and have a look at the design I'm using quickly. This is it. It's pretty straightforward. It's just the microcontroller, a bunch of LEDs, and an individual resistor on each of the LEDs. And I'm doing it that way because I want to have the ability to put on multiple LEDs at the same time. And then I have two header connectors. One is focused on the I2C interface, and one is for the programming and the power side of things. So nothing complicated in that design. For the PCB itself, let's turn on all the layers. Hide some of this garbage here. So the layers you're going to need for a single-sided board are as follows. You're going to need this front-sided copper layer, the FCU layer, just like that. You're also going to need this F paste layer, and then you're going to need the F silkscreen layer, like that, which is the front silkscreen. And I'm also demonstrating burning into the blank side of the PCB, the backside silkscreen as well, which is not actually a silkscreen in this case, it's a burn-in we're going to do. And then we have the front side mask, which is what we're using to burn and clear all of the pads. And then I have two other layers that I'm using, which are custom layers, which is this layer 8 here. So this actually shows the area of the edge of the board which I want to clear some resin, and that sort of avoids the edge of the board getting chipped easily. So you can see it's right on the edge of the board there. And then I'm using this layer 9. That is actually for the shape of the PCB. Now there is a layer here called edge cuts, which in theory should do the job, but it did have a couple of problems when I tried to use it, so I'm not using that. But you do need to define the edge cuts, because when you're filling an area in the PCB like this, the edge cut is what sort of limits the extent that the fill will occur in. So you still need to set the edge cuts, but these additional two layers for the clearing the edge of the board of the resin and the actual shape of the board, which we need in the process, also needed to be defined. So yeah, you need those. And if you take a look here, you can see that I've actually got the PCB located here above the frame. It's really a bit strange, to be honest. And that is because by putting it in this coordinate location, I can use the exported files just as is when I import them back into FlatCAM. If we actually have a look at some of the coordinates here, let me just pick one of these objects. Try and simplify this down. If we double click here and have a look, you can see that the Y coordinate is actually negative. So it's 0 and running negative. but when we import it into FlatCAM, this actually turns out to be positive. So I don't really understand why it does it that way. And to be honest, I spent some time trying to figure it out, how to use this in a more sensible fashion, but I couldn't actually do it. So maybe if somebody out there knows the answer to how to do this properly, they can tell me. But for now, this is a very easy and simple way to solve the problem, and I don't really care about that frame in any case. So this has been working quite well for me. You can actually reposition the offset within FlatCAM for every single layer, but as I said, that's very time consuming, and every time you go to update the PCB, you have to do that as an additional step every time. So that's why I don't do it that way. I also am just using for layout purposes 2 other layers here, which I'll just show you. This user 1 and user 5. I could have stuck it all on the same layer, but for some reason I stuck it on this layer. And I do this just to draw the shape of the piece of the board that I want to use, or the blank piece of the board that I want to cut out. So this helps me figure out the dimensions, 35 by 33 in this case. I don't know why I've put these dimensions on the edge cuts, but anyway, that's wrong. And then I've also got here, you can see the location of where the clamps will go on the job as well. So that gives me an idea of how it's all going to fit into the working area. And so when I export the job, the 0 origin is directly relative to the origin of the blank PCB. So I can just locate the laser in that corner, and it will locate the work in the right place. And just one other little thing that's a little bit unique that you're going to have to pick up here as well is that as part of the process, you're going to need to drill some locating holes. And I'm only drilling 1mm holes. You can see on the left-hand side here, I have those 2 markings for where I want to drill those holes. And when we are working in FlatCAM, we will actually enter the coordinates manually of these holes, and the right-hand side will automatically be mirrored. So we only need to get these left-hand side. So what I typically do is I just roughly place the location of these marks. I think I'm putting on layer user 1, and I will just write down the X and Y coordinates of the 2 holes, put it in Notepad or something like that, and that'll allow us to reuse it later. So I will actually just take note of that now. 5 by 4, and the other one is at 5 by 28. All right. So let's also take a look at some of the basic settings so you can use them as a reference when you're doing your design of your PCB. Obviously it might vary, but at least you can sort of see what I'm using. So for the tracks, the classes of the tracks that I'm using here, you can see the default size is 0.12mm clearance. So for all of the signal tracks, they'll have a clearance of 0.12mm. And the track width is at 0.13mm. For the ground and the power, it's a little bit different. I've widened up the clearance just a little bit, and I made the tracks a little bit thicker. For the ground, you'll see that it's actually not as thick as the power, and that's because the ground track will actually be used as fill layer or be connected to the fill layer. So that's going to mean it's going to be a lot wider anyway, and just having that smaller track width here makes it a little bit easier when I'm designing the PCB. And if we have a look at the fill area here, you can see I've sort of got it roughly drawn around here. The settings for the fill area, you can see that I've got it selected to be operating as connected to the ground. The clearance is basically the same as what the power tracks are. So we have 0.2mm clearance, and I have a minimum width of 0.1 so I can fill into all the nooks and crannies. And you can see that I'm also removing islands if they're really, really small, below 0.25mm. Actually, when I'm designing, I usually set this as always remove islands. And let me just show you what that looks like. So if I refill, I'll press B, that'll fill. You can see here that only these 2 little areas here aren't filled in. So this is the point. When I'm doing the design with the islands turned off, I make an effort to fill in the board with the ground plane as much as possible by pushing the tracks around as need be. And in this case, these 2 little areas were all that were left that I couldn't actually fill in with the ground plane. So once I get to this stage, then I'll get back into here and I will turn the islands back on, but obviously they've got to be above a certain minimum size limit. We press B, we get those 2 little locations filled in at the last. So I think the key point is just to know your minimum limits. With my current setup, my minimum limits is that clearance of around about 0.12mm. So when you burn the track at that size and you etch, the smallest size of separation I can get is around about 0.12mm. And then there's the issue of your smallest track size. And as I said before, I can get it down to 0.1mm, no problems. And I do use that on the occasion. But you have to be a little bit more careful when you're etching, because if you over etch it, you're going to lose the track. So typically I'm sort of sticking to 0.13mm as my minimum size of track width. And that just gives me a little bit more comfort when I'm etching. So once we've got the design finished, I suggest a couple of things to do before you actually go and export the files that you need. The first thing is I really like to have a look at this 3D viewer here. and I recommend you use it because you can get a really good look at how the tracks look and how they fit together. It's a little bit difficult for some reason to see it with all those layers packed on top of each other in the designer view, but here you're just seeing it as a raw board, as a finished product, and I found it's really good to sort of identify issues with tracks or layout or the design or something that looks a bit ugly. You can pick it up pretty quickly and you can get a good feel for the general sort of layout. I mean, designing PCBs is a bit of an artwork, so you should treat it that way, I guess. Well, I do anyway. And you can see that most of the components here have correctly been sort of identified and located automatically by KiCad. I noticed the microcontroller, this WCH series microcontroller, doesn't have the QFN package there, but it's only a small minus, I guess. So the pin headers on the back here and everything, and it looks really good, I think. So yeah, I highly recommend this. As I said, I've managed to pick up quite a few issues just by looking at this and sitting it, spinning it around for a few minutes before I finally settle on the design. The other thing that I recommend you use is there's this design rules checker, and that's going to check a whole bunch of stuff, probably too many things, but what I typically do is just turn everything on and then run the design rule checker with this button, run DRC, and it goes off and does its thing. And you can see here I've got a whole bunch of errors here. I don't even know what that is there, so ignore that. Actually, this is because I've got this garbage on the wrong layer, so I'm just going to delete this for now. Run it again. And you can see these all sorts of errors. I mean, most of them are all these courtyard overlaps because I'm really pushing the design, and they're not really issues if you know they're not issues. I mean, obviously you look at it and check it and make sure that there are no issues. And there are a few things where I've modified the labels on the Silkscreen overlap errors. So there's nothing really here. That's because I've already fixed it. But where it really can help is it will tell you if you've got any disconnects or if tracks are intersecting each other unnecessarily and things like that, or if you're too close beyond the set rules for a given class of tracks. So it's a really good way to pick up on issues very quickly. So anyway, as I said, recommend you run it, check it, try to understand what the errors are, and if they're a problem or not a problem, you're gonna have to make a decision. And once you finish, you can just delete all the markers with the delete markers button and you're done. All right, to output the files, we just need to go to File, Fabrication Outputs, Gerbers. Now you need to set your output directory. In this case, I've got it as PCB output / I'm not sure if that's a default name or the one I gave it, but if the directory doesn't exist, it's going to make the directory. And as it says, as it's written here, this is a relative directory. So this will be relative to the project directory that you have. So in this case, this is the project directory, so it will be automatically created in here in a second when we make the Gerbers. The plot format's got to be Gerber. All these other settings here you see, I don't actually remember what I might not modified it. I'm pretty sure they're all default values. But anyway, here they are on the screen, so if you want to follow what I'm doing here, that's fine. And the layers that we're exporting for this single-sided board is the FCU, the F-Paste, F-Silkscreen, B-Silkscreen, F-Mask, and the user 8 and 9, which are those special layers which I discussed earlier. So once you've got that all selected right, hit the plot button. Sometimes it complains that you haven't done the fill or updated the fill, and it'll prompt you to do that. Just press yes and go on and ahead and you'll be done. So let's have a look at that folder. There's that new folder created, and here are all our Gerber files that we needed. I don't know what this job file is, but it's not really relevant, I guess. All right. And now we also need to generate the drill files. And we need to generate the drill files in two formats. Again, you need to specify the output folder as well. Again, relative or specifically the exact address. We need to only create the drill file. We don't need to make the map file. So this is the drill file format here in the top left. And we will export it in those two formats, in the Epsilon format and in the Gerber X2 format. So to do that, for example, you select the Epsilon format. And again, you can see the settings for that here. I'm pretty sure, again, I haven't messed with them, so I'm pretty sure they're default, but you can see as they are. Then you press the generate drill files, and that's done. And you'll see there's two types of files that are being created. One is the PTH and NPTH, right? So the PTH is plated through hole, and the NPTH is the non-plated through holes. So I guess if you're having holes such as the mounting holes, they'd be non-plated, in some cases anyway, I guess. So they'd be the NPTH. But for primarily everything we're doing, even though we're not going to plate the holes, it treats them as if they're plated. So the PTH file is the one that we want. So we've created them as the .drl or the Epsilon file format. And then we're going to create it as the Gerber format. And I don't know why it says Gerber X2, but I guess whatever, that's fine. That's the one we want. So we need it in a Gerber format as well. So we'll create it. So now we have a look at those files, and hopefully we can see the drill files here as well, right? Properties. Yeah, so these top two here are the drill files, and the bottom two here the Gerber files. All right, so we've got everything we need, and that's it. That's everything we need to do in KiCad. So let's move on to the next step. Alright, so KiCad outputs the intermediary geometry files, but it doesn't actually generate the G code we need to use with our CNC. So to do that, I'm using FlatCAM, actually FlatCAM version 8.994, and it's apparently some sort of beta version. It says beta at the top here. So yeah, I'm not sure what's up with that, but anyway. So this is actually an open and free software, and I'll just get the website up here for you to look at. Yeah, so this is it here. Looking at the website, you can see it looks like it's been pretty silent for a while. You can see that the last information on the website is like for version 8.4. And originally I actually tested what it was talking about on the website, which was version 8.4, which is apparently an official release. But that thing was totally unusable. I mean, the basic concept was there, the graphics and things like that was there, and it was looking promising, but it was pretty much, I'd say, unusable in that form, that's for sure. So if we go to the download page, and you can see it links you to this bit bucket, we can actually see, it looks like this Juan Pablo Caram is the original sort of leader of the project who was doing the releases anyway, so it's not really sure who's doing what, but I'm pretty much sure that, you know, that these individuals are the ones doing most of the work on these projects. So he was sort of pretty busy up until 2015, 2016, but it was really sort of finishing on that versions 8.4, 8.5, which are really not really, you know, usable form at that point. And things sort of go silent for a while, and we see that this Marius Stanciu seems to pick up the baton. I think he's from Romania or lives in Romania. Anyway, somehow he's sort of taken the lead on the project, and he had released quite a usable version in 2020 onwards. And you can see that the installation package for 8.994 has been released as recent as middle of 2023, so there's something sort of happening there. In any case, the 8.994 is actually a really quite a good piece of software. It's very usable, and it, you know, I can highly sort of recommend it in that sense. I mean, without that piece of software, it would have been pretty much impossible to do what I'm doing here. So yeah, definitely pretty good. Unfortunately, it still smells like a bit of a work in process in a few areas. The UI is a bit rough around the edges, and there's some terrible sort of custom UI settings and things like that, and features that are buggy, and the occasional fatal crashes as well. So, you know, it is what it is. Unfortunately, as I said, it doesn't look like it's being updated all that recent, that's for sure. So this is definitely one of those places where I also would recommend that if you're using the software and you found some way to make a donation to Juan Pablo Caram or to Maria Stanciu, then, you know, I would definitely recommend people making an effort to try to do that. Unfortunately, I don't really see the obvious way to do it in the information that's on this website. But I think one way or another we should be showing our interest in this software, and you know, you never know, hopefully, you know, maybe the development and support might pick up a bit again in the near future. Alright, so now you have the lowdown on what FlatCAM is and where it's at. Let's actually start making the files that we need to drive our CNC with. The first file we're going to make is the G code for burning the pattern in the resin layer that we require for doing the etching. So let's do that. So file, open Gerber. We need two files actually. We're going to open the copper layer file, and we're going to open the plated Thru-Hole drill file, the Gerber version of that file here. So two Gerber files will open together, and there they are. You can see them layered on top of each other, the pattern and the drill file. And what we need to do is subtract that drill file from the actual design. To do that, you need to press Alt-W to get to the subtract tool, and the target is going to be the copper layer that we're dealing with, and the subtractor is going to be those drill holes. And we're going to click this checkbox for deleting the source because we don't need to leave the old files there, which is nice in this case. So then we click the subtract Gerber, and bingo bango, there you go. You can see the holes have now been opened up. So I prefer to open up the holes, and I only figured out how to do this recently, and this works really well. All right, so the next thing we're going to do is we're going to do some etching compensation. And there is actually a tool in here to do that, which I tried using, and I got sort of mixed results, and sometimes it sort of crashed. It looks like it sort of isn't complete, so I don't recommend using it. And there's an easy way to and a more sort of logical way to do it without having to use this tool, thankfully. So double click on the Gerber file, click on the Gerber editor, and there's two things that we want to do in here actually. The first thing is we want to make sure all these holes are actually clear. What I found is that in KiCad sometimes when you draw the track, it will sometimes draw a little bit of track inside the pads, which you can't actually see. If you select over the pad, you'll see it sometimes and you can delete it, but more often than not, you'll end up exporting it. And the subtract tool, for whatever reason, doesn't subtract those bits of track and they'll be left over. So if you do have the case where there's little bits of track that are left over, you can either fix it in KiCad and re-export it, or you can just select those bits of pad in here and delete those little bits of elements. So in this case, I've already fixed my KiCad design, so it doesn't do that, and so there's nothing to do in that regard. But what we want to do here is that etching compensation. So we select everything and then we hit this little B icon or the buffer button here. And what we're going to do is fatten everything up a little bit. And the amount is 0.022 millimeters, which is the number that I've come up with. That's as far as I can really push it basically with the current way that I'm drawing these tracks. So hit the buffer button, you'll see it all sort of fatten up a little bit. Exit the editor, save it. And now if we zoom in, you can actually see the two files overlaid, the original file, which is the smaller one, and the buffered or the larger file, and filling it out quite a lot. So the Gerber object that is by default shown is the one that we edited, so the sub underbar edit here. So from here on, we can move straight to the isolation routing. The thickness of the laser is actually a little bit of a tricky question. It's actually oval in shape when it burns. And I've measured it, the burning path. It looks like it's around about 0.06 millimeters by 0.09 millimeters, something like that anyway. So I sort of choose a number in the middle, and so that's 0.075. And then we want to have the number of passes or the number of times that it will burn around a feature to create the geometry. And in this case, the key thing is likely the outside of the board, where we want to create about a 1 millimeter clear amount of burning path, which is necessary because that's where I will cut the board with the laser later on. So we want to have a good bit of space there. So I found that around about 19 passes with a 33% overlap. I'm actually using 33.3333% because a 33.3333% is around about a 0.025 millimeter overlap. And with that amount of overlap, given the fact that the burn path is actually oval in shape, that is just enough to ensure that as we clear the resin, there shouldn't be left anything behind, or if there is, it'll be so thin and so small that when it etches, it'll just pick it up and drop it off anyways. So 0.075, 19 passes, 33.333%. Generate geometry button, we'll click that. Now at this point, we want to check the geometry. We want to have a look and make sure that everything is isolated properly. If you have any sections in between the green here where there is no red lines, well then there's not going to be any burning and you're going to have a disaster. So that's the main thing you've really got to pick up. And you'll see where the smallest possible isolation that we have are where these two lines are overlapped. So you'll always have two burns on any separated element, and that will guarantee that we're going to get that etching occurring there. But you'll see in these wider features here where there's a wider gap, and that's with that 33.33% overlap. It's a little bit different, but this is still correct and it will still etch quite fine. On the outside here, we have enough cycles going around to give us that 1 millimeter sort of burn path. All right, so I know this is good because I've made about 1,000 of these boards. Let's move on and actually set it up and turn this geometry object into a G-code file. So the first thing you've got to do always when we're dealing with these laser jobs is select the preprocessor, because that's what's going to get rid of nearly most of these unnecessary drill-related options such as depth and all that sort of stuff. So go to the preprocessor, select GRBL laser. I'm assuming you're using a GRBL machine. If you're not, well, you're going to have to figure it out. So now all of the unnecessary stuff's gone away. There's still a little bit of unnecessary stuff left, but we're just going to have to live with that. I'm not sure how necessary it is setting up the V-tip information, but I set it up anyway just because, well, it seems like the right thing to do. So V-tip diameter is the diameter of the laser, and the V-tip angle, well, there's no angle as such. Well, there is actually a little bit of angle, but anyway. Just say there's no angle in the laser, so I set it at 1 degree just to set it to something, I guess. The feed rate I'm using for the laser for nearly all of these G-code jobs is 650 millimeters per minute, and that's as fast as I can go to get a very clean finish and accurate burn. In my old rig, I could push it only up to about 500 millimeters per minute, So I actually have gotten faster. And actually with my new CNC, not only have I gotten to go a little bit faster, it's actually even cleaner than it was before at the old 500. So the upgrade of the CNC has really done a good trick on cleaning up the burn path. Even so, even if you have a basic CNC 3018, you'll still get a pretty good result, as you've seen with my prior episodes, but you'll probably have to slow this down a bit and modify the power settings as need be. So anyway, 650, the laser power I'm using in this case is 50% or 5,000 RPM. I think that's pretty much it. Generate the CNC job, save the code. Now we need to click the project tab. And what I do after every single file that I create is I hide all the stuff that I've done and I save the projects just in case it crashes, basically, because it does have a habit to do that. So to hide all of this stuff, the easiest way to do it is press Control A for selecting all, right click on one of them, disable the plot, and wait for it to disable all those plots. So Control S. So this is the first time I'm saving it, so it's giving you the option to put in the file name. I'm just going to use the default file name, press save, and we're done. Next time we save it, it won't come up with that dialog box. It only does it once. Alright, so the next job we're going to make is for the front side Silkscreen, where we're actually exposing resin onto the surface of the PCB. So for that, we're going to open up the Silkscreen Gerber file for the front, Silkscreen, and we're going to go straight into isolation routing, but instead of isolating on the outside, which would be quite useless, what we're going to do is just create a little thin outline first, and then we're going to do a job to paint inside of the geometry that we create. So let's just do that. We're going to use a very fine diameter tool to create the geometry. One pass just on the outside, 0% overlap, and that will just create that little outline for us. So generate that geometry, and you can see it's sort of gotten dark here. This is a red line on the outside, just on that outline. Now we're going to paint inside that. And the setup for this is also a little bit special, so let's do that. The exposed resin width is actually only about 0.1 millimeters wide. It's probably a little bit bigger, but that's what I'm using for the tool diameter in this case. We don't want to have any overlap because it's a nice thick exposure in any case. And the offset I set at 0.01 millimeters, so that just pulls it a little bit to the inside of the outline geometry when it paints it in there. The other thing we want to do is we want to disable this connect and this contour because we don't want to draw the outline, we just want to draw inside, and we don't want it to continue to draw the line as it moves from one point to another inside the object as it's painting, otherwise that will actually overexpose. So we need to disable both of these, connect and contour. Alright, so that should be right. Let's generate the geometry. And we can zoom in and take a look at how it's done. On the text here, you can see how it sort of leaves a little bit of a gap as it runs the two paths to generate, say, for example, any of these characters, which is fine, shouldn't cause a problem. And on the thinner line here, it's literally overlapping the two lines, so it's just going to make it just a little bit tighter. And for this triangle where the geometry is a little bit bigger, you can see how it's sort of doing two passes, but that will still come up with a solid triangle when we expose that. So I think it's looking all pretty good. Unfortunately, with the paint tool, after you've generated the geometry, it doesn't send you on to the next stage. You have to do it manually. So we go back to the project tab, and now we have to double click on that newly generated geometry, the paint geometry, double click there. And now we can set up the CNC job. So first thing, preprocessor. Always remember, set the preprocessor GRBL laser. The tool 0.1, oh, it's already 0.1 anyway, so I don't need it. Diameter 0.1, angle 1. For the XY feed rate and the laser power, this is the tricky bit because we're exposing, we're not burning in this case. So these are the settings that I've come up with, which worked for me. Obviously, they might vary again for you a little bit. But for me, I had to slow it down a lot. So the feed rate is only 200. So it takes a little while to complete, but there's not actually a lot of stuff to paint here. So it still completes in a few minutes. And the power level is only 4.7% or 470 RPM. And actually, I was very surprised about the very narrow range of usable laser power. It's literally in a 0.1% to get the optimum laser power, and it took a lot of sort of tuning to get it there. So you have to be a little bit persistent with finding that point. But once you have it, it works perfectly every time. And the difference is whether it will stick well to the board or it won't stick well to the board, or if it's just way too overexposed and too thick and chunky. So, you know, you really have to find that point where it's as nice and clean and thin as possible, but not so thin that it won't be exposed enough to stick well to the board. So anyway, this is what worked for me, 470. As I said, it's probably going to vary for you, but it can be done. Once it's right, it will definitely be right. All right, so we generate the CNC job. Save the code. Now if you click back to the project tab, Control A, right click, disable plot, waiting, Control S, saving. Alright, so next up we're going to create the job for removing the resin from the pads. This has always been a bit of a bane of my existence, but I finally figured this out. So let's just create the job and we'll talk our way through it. So in this case here, we actually need, again, to open up two files. We need to have the mask file and we want that plated Thru-Hole's drill file as well. Okay, so now we have those two and we're going to go straight to that subtract tool, Alt-W. We want to subtract from the mask, the holes, delete the source, subtract the Gerber, and there we go. So now we can double click on that modified mask file. We're going to go to isolation routing and create an outline for all of these pads, similar to what we did with the Silkscreen. Well, similar but same, actually. So that'll create the outline geometry. And now we're going to go into paint and we're going to paint inside this. Now the paint is quite a bit different because we're actually burning the pads. So let's just set it up. The tool in this case is the 0.75 because we're just burning the resin, the same as if we were creating the etch pattern. The overlap that I'm using is 33%. And the offset that I've come up with is 0.0128. So the overlap is similar to creating the pattern for the etching of the copper layer, 33%. So making sure that we clear all the resin off the pad. But the offset is more about managing the resultant pattern. So the pattern that I'm using, and I'll select it here, is not the standard one. We're going to use lines. And with lines, it's just drawing a set of horizontal and sometimes vertical lines, depending on the, I guess, the proportions of the pad that it's filling in on. And we're going to turn off the connect method. And that's really critical because if we leave the connect enabled, it will continuously add power. So it actually goes from left to right, for example, goes up a little bit and then right to left and just keeps going up until it clears the pattern in that manner. The problem is that the laser stays on consistently throughout while it's clearing the pad and it's consistently heating the pad, and that can make it more likely you're going to damage the substrate of the PCB. So by turning off the connect method, what happens is that as it's clearing, it will draw one line and then it actually moves diagonally back again to the other side without burning. So that gives a little bit of a rest time as it moves back, and then it burns left to right and moves diagonally, no burn, left to right, and so on. So this is a strategy to reduce the amount of heat being pumped into the pads over time. Now we do leave the contour or the outline enabled because if we only draw the lines, it just leaves sort of like a nasty jagged edge and it's not very nice, so we leave the contour on. And coming back to this offset amount, let me just generate the geometry and I'll have a look, and it's a better way to explain it. So we've got everything set up, 075, 075, 33, 00128 lines, no connect, contour, generate geometry. All right, there we go. So let's have a zoom in and have a look. So we can see the effect of the offset where it's actually pushing it in a little bit. But I've tuned the offset so that it works well with my design here, so that I only get, for example, these 1, 2, 3 lines on these smaller pads. And that's important because if it's like 3 and a bit, well then it will actually draw one extra line just down below here and it will double up on the heat just in one portion of the pad, which can be damaging. So this is the number that works for me and my designs. If it was a different design, maybe I would modify the offset just a little bit to get rid of any weird patterns. But this one works well. If you look at all the pads, they all sort of end without any half drawn lines or anything. So the outline is the outline pass and all the lines in the middle are the lines passes basically. So yep, that's painting the jobs, and you can also see that, yeah, so these different proportional pads, this one's here where it's taller than it is wider, it means that they're drawing the lines vertically, where it's wider than it is taller, it's drawing the lines horizontally. I guess that's the way the logic works. Alright, so now we've got the painting done, let's create our G-code file. Obviously we have to go manually back to the project tab, select the paint job, double click, and now we can create the CNC job. So preprocessor, laser, GRBL, 0.75 for the tool width, 0.75, 1 degree diameter, nice constant 650, and the laser power they come up with is 44% or 4400 RPM. Alright, so we'll generate the CNC job, save the CNC job, go back to the project tab, Control A, disable plot, Control S. Alright, so the next one is for removing the resin from the outside edge of the PCB. So let's get that file for that. File open Gerber, user 8. And in this case again, we're going to have to do an isolation routing to get the outline of this object. Isolation routing. So, very fine tool, 0.0001. No overlap, generate geometry, and now we have the outline. Now we go straight to the paint tool, and we're going to paint in here. Alright, so we set up the tools. It's just a laser, so 0.075. Overlap at 33%. And again, we're setting this offset up to be some weird value that sort of makes the pattern, the resultant pattern, look nice without any weird sort of close lines or overlaps. And we'll have a look at that again in a second. In this case, I do enable the connect because that sort of seems to work well as it sort of rotates around the circle in this case and comes back and has to move to the next one. I notice when I turn the laser off and on after the move in this case, it seems a little bit overburn compared to leaving the laser on during that move. So in this case, I've decided to leave the connect enabled, and we're also going to keep the contour enabled. All right, well, let's generate this geometry and have a look at what that looks like. We can see it's a little bit offset from the inside here as per the offset, but we can see that we've got nice even spacing on all the burns, which is what I'm looking for in this case. So we'll go back to the project tab, we'll select that painted object, and we'll set up the G-code job. GRBL laser for the preprocessor, 0075 for the tool, 1 degree, 650, and the laser power in this case is quite low, it's only 20%. 2000 RPM, and that's because we're just really sort of scraping off about 50%, or I think it's around about 70% of the surface of the UV resin so that it just thins it out in the edges of the board. Anyway, that's what I've come up with, and that's what we're going to use. So let's generate the CNC job and save it. Go back to the project tab and let's hide everything again. Disable plot, Control S, save the project. So next up, we're going to actually create the job to cut the board. So I've done a lot of experimenting with cutting the board, and what I found is that it really doesn't matter how many times I run the laser over the board, I can only really cut to around about 1/3 of the depth of the PCB. So the way that I've been doing it, even in my earlier videos, and I quite like it as compared to using the mill, is to burn that 1/3 depth on one side of the board and then flip the board and burn the 1/3 depth on the other side and then just snap the PCB out with that remaining 1/3, or I think it's less than 0.5 millimeters of connection left. It's pretty easy just to snap it out, and then I just clean it up with the files. This job that I'm making here will be cutting the front of the board, but if the PCB is symmetrical, you can use the same job for the front and the back. But for this demonstration, I'm actually going to do the process of creating both separate files, just so that you can understand how you might deal with it if you've got some weird L shape or some strange shaped PCB. All right, so let's make the front side cut operation first. File, open Gerber. The user 9 is that shape of the board itself. We'll go straight into isolation routing. And the setup is actually not that complicated, even though it's a little bit tricky what I'm doing here. But anyway, let's just do it. 0.1, 0.1, we're just going to leave as is because burning is actually quite a wide operation compared to actually just engraving with the laser. The passes count, we will set at 22. So we're going to burn around the same spot 22 times. Now, if you've seen the isolation routing we set up for the copper layer, for example, that means it will sort of move out, and out as it's burning. But we can avoid that by changing the overlap so it overlaps 100% of the time. But I don't think we can set 100% here. So what I'm setting here is 99.9999% of the times. And that means that basically it's overlapping 100% of the time. So 22 times it will just sit there and burn around in a circle. So you can actually do as many times as you like if you want to experiment and see if you can get it to cut deeper. I actually found that after about 19 passes at this setting, it's pretty much as deep as it's going. So I've just thrown in 3 extra burn rounds just to try to get a little bit more out of it. But it just gets to 1/3 depth no matter what you do. It's just the way it is. All right, let's generate that geometry. And we don't need to do any painting or anything because this is basically the job as it is. All we need to do is just create that G-code job. So set up the preprocessor, GRBL laser. The tip, 0.1 can stay the same. 1 degree for the angle of the tip, meaningless setting, but anyway, 650 feed rate, keep it all the same. And 100% laser, or 10,000 RPM. Okay, let's generate the CNC job, and done. Save it, save to the project. All right, let's hide it, Control A. Now, if you're wondering why I'm sounding a bit tired, it's because this is the second time I've recorded this. I'm buggered after doing this twice. Anyway, let's keep going. Hide it, disable the plot, or lose the plot like I'm losing it now. Control S, saving the project, all done. So that's pretty much all the laser operations on the front side of the board. All right, so next up we're going to do alignment holes. And these alignment holes are used for when we're flipping the PCB and realigning it on the other side. I'm using a bit of a different process for doing that. What I'm doing is just drilling very small 1mm holes into the PCB and then actually burning a laser circle inside those holes onto the work surface. And then you can actually pick the PCB up, flip it over, realign it to the burn marks, and there you go, you've got a aligned PCB, and it works really well. So let me show you how to first drill those holes. We're going to enable this user 9 Gerber file first so we can see it, and we're going to open up the double-sided PCB tool. So Alt-D gets you into that. Let's select the source object as being the user 9 layer, which is this outline shape of the board here. And we can press the calculate bounds value, and I just press it and nothing's happening. This happens with this tool sometimes. It just doesn't recognize what you've selected. So what I do in this case is I go back to the project tab, I disable the plot, enable the plot, go back to the two-sided tool, and yeah, solves it every time. So you'll probably run into that bug too. It's a bug, but it is what it is. Anyway, after we calculate the boundary values, we get all the x min, y min, whatever, that's all irrelevant. What we want is the center of the object, which is here 17.5 by 16.5, and that value is also populated into all of the other PCB alignment and mirror operation values as well. So what we've done here is just get that center value or the center XY position of the PCB that we can then do our mirror related operations on. In this case, we're going to use the PCB alignment component of this tool. That's why this UI is so confusing, how it's got all this mix and mash of stuff in here. But anyway, the PCB alignment is what we're going to be dealing with. I'm going to be drilling a 1mm hole, and we're going to do a mirror operation using the y-axis. So if we draw a line vertically, that's where it's going to mirror. So we only need to give the coordinates for 2 holes on the left side, and on the right side they'll automatically be mirrored once we create the epsilon object. So to create the coordinates, this is a little bit, again, a bit fudgy, but we'll just do it this way. What you do is just click on the surface, and then you click add, and it gives you the first coordinate, and then click in the other place that you want to have the hole drill, and click add again. And now we have the 2 coordinates. Now these are not the exact coordinates that I want because I wrote them down earlier if you were paying attention when we were doing that KiCad part of the video. So let me just get the values that I wrote down earlier. So x is 5, y is 4, and x is 5, and y is 28. This is what I had set up in that KiCad sort of layout. So those are those 2 left-hand side holes that you saw in the design I drew earlier. Now we're just going to hit the create epsilon object. And there we go, we've got all the 4 holes surrounding the object. So what we need to do now is set up the drill job. So let's go back to the project tab. We can see that the epsilon file has been created here, alignment drills. You can double click on that and then go to the drilling tools button. And this is really very easy. This is probably one of the best areas of the program. I don't modify that much, but I do modify a bit. The Z depth I'm using is a little bit deeper because I want to clearly drill the holes, and sometimes I find if I use minus 1.7 millimeters with those 1.5 millimeter thick boards, it just leaves a little bit of garbage left behind, so that's what I'm doing. I also tighten up the Z travel height to be a bit shorter, so save a bit of time, 1.5 millimeters. Feed rate, I leave it as it is, and I just run my spindle at 100% speed, which is actually around about 10k in reality, so 10,000 RPM. And other things I modify is the end move on the Z axis. I move the tool back up out of the way, 25 millimeters, and then I move the tool to the 0, 0 coordinates in the XY plane, 0 by 0. And we need to select the preprocessor, GRBL 11, no M6 is the one that you want because this is not the laser operation, this is a drill operation. Generate the CNC job, save the CNC code, back to the project, Alt A, disable the plot, Control S, save the project. Alright, and while we're doing drilling stuff, let's move on and make the drill holes for the job as well. So I'll open up the epsilon file in this case, so open epsilon. Plated through holes is the one we want, the PTH file. There we go. I only have one size of drill hole in this case, so it's not a very complicated job. So we'll just double click on the epsilon file, click on the drilling tool, and it's very much similar to what we just set up. 1.9 for the cut depth, 1.5 for the travel, 10k for the spindle speed. If you have multiple drill sizes, you can set it up to have a tool change. You just enable the tool change. I recommend using a 25 millimeter tool chain height. And obviously, if you are using multiple bits or multiple tools, you'll need to make sure you have those little rubber stoppers so they're all adjusted to the same height so you don't have any depth variation as you're drilling. And typically what will happen is it will go through and it'll do the first set of drills, and then it'll go to the tool change position. You change the bit and then you press the play button again. It'll go to the next one and the next one and the next one until you're done. So that works pretty good. I've used it a couple of times. So if you do have multiple sizes, I do recommend doing it in the one sequence if you can. All right, but I don't have a tool change, so I'm not going to change that. I will change the end move to the 25 as I did earlier. 0, 0 at the end, move for the XY plane, and the preprocessor as the GRB11, no M6. All right, let's generate the CNC job object, save the code, save, back to the project tab, Control A, disable plot, Control S. So the next bit is actually burning the laser marks inside those alignment drill holes that we made earlier, the job for. So to do that, what we want to do is just select the alignment drills item, but don't enable the plot. And then in Edit, Conversion, convert any to Gerber, select that, and that will convert the Exelon file, the alignment drills file that we created, into a Gerber file that we can then use. But we do need to take one more step because the size of the elements are a little bit too big. If we just burn a laser around the edge of the holes, it's going to burn it on the board itself. We need to burn inside the holes. So what we're going to do is we're going to edit this file with the Gerber editor. And we could use that buffer tool, but I found the easiest way to do this is just to double click on this aperture size here. And if we just change that to 0.8, it modifies the size of all of those objects because they all seem to use the same aperture code for some reason. I don't really know how a Gerber works, but this seems to work. So 0.8, and if you watch carefully, you'll see them get smaller. Yeah, so there we go. So exit the editor, save it. And now we just need to do the oscillation routing. You can see the new smaller size file that we're dealing with the edited version. So click on isolation routing, and obviously we don't need to do any painting or anything like that, but we do want to draw the line right on the path. So we're going to use a very fine tool setting, 0.0001. It's a fine tool setting. We only need one pass, no overlap. So it's a very, very simple isolation routing setup, that's for sure. Generate the geometry. And now we can just go ahead and create the G-code. GRBL laser as the preprocessor. The tool, we need just to modify that. 0.075, 0.005. 1 degree V-tip angle, 650 on the speed, and I found that 3000 or 30% power is just enough to sort of burn onto the surface the marking that I need. Now I'm not actually burning onto the wasteboard. I actually lay down a layer of masking tape and I'll burn onto the masking tape. It's actually a little bit difficult to see, but it works. It works pretty good. All right, so let's generate the CNC job, save it, back to the project, Control All, disable the plot. Yeah, now it's gone. So now we're going to start doing some work for the backside of the PCB. So for the backside of the PCB, we actually have to mirror everything. So if you were doing a double-sided board, obviously mirroring is a step that you need to remember to do before you actually process any of the files as well. So just keep that in mind. But anyway, in this case, we're going to use the Silkscreen for the backside of the board. So for the back side of the board, we're actually going to burn this into the non-copper side of the PCB, or the raw sort of resin side of the PCB, and we burn in the mark pretty deeply into that resin to make it quite visible. And also to make it quite visible, I've made the size of the graphics a little bit larger, both in the width and in the font size. So if we compare it to the front Silkscreen, you can see it's quite a lot thicker and it's quite a lot bigger as well in the design. So that's just one thing to keep in mind if you want to use this feature. All right, but for now, the major problem that we have is we want to mirror this because we can't burn this like this because this is looking at the graphics from the top, but we're going to take the board out and flip it, and we want to look at it and burn it from the bottom. So we need to mirror this design. And to mirror it, we need to have some center point. So this is where we're going to enable this user 9 layer again, enable the plot. And this will be our reference that we'll use to flip the graphics. So we're going to use the double-sided tool again, so Alt-D, and then we're going to use that user 9 layer to calculate the bounds and get the center point, because we can't calculate the bounds from the graphics because that would cause it to be all out of whack. And again, it didn't work. Disable plot, enable plot. Calculate bounds, there we go, nice and done. So now we have the boundaries. We have to remember to reselect the source object. We need to select it back to the graphics because that's the thing that we want to mirror now. So here's the mirror operation in the middle here. This is really weird how they laid out this user interface, but anyway. So the mirror operation, we want to mirror on the y-axis. So that's the way we will physically flip the board. Click the mirror, and there you go, it's flipped. So we go back to the project tab, you'll notice that it doesn't actually create an extra file. It just modifies the original file, which is a little bit inconsistent compared to what they do for when you're editing or doing any other operations. But anyway, that's just something to keep in mind. It doesn't really cause a problem and creates less clutter, so I sort of don't mind, but I do mind the lack of consistency, but that's just my little rant, so don't worry about that. Alright, so let's get on with doing the isolation routing. Double click, isolation routing. It's very similar to what we did with the exposed type silkscreen. We still need to create the outline so that we can paint inside it, or burn inside it in this case. And the method to create the outline is the same. Use a fine tool with one pass, no overlap, generate the geometry, and now we have the outline. And now we go to the paint tool. In this case, for the paint tool, the laser burn width, we're going to set it up at 0.075. The overlap I actually leave at 20%, so I leave a little bit of overlap when we're burning. I'm not setting any offset. I'm still just using the standard sort of method for filling it. I do, however, turn the connect off because we don't want any double burning as it moves around. It's painting inside the object, even though that's probably unlikely, but it can happen. But we will also maintain the outline contour of the burn as well. All right, let's generate the geometry and have a look at it. So you can see all of the paths that are created as it's sort of burning. And they're quite even and nice, and that's sort of what I was targeting for. That's not very even and nice here. It's probably because the font's a bit of a different size, but you get the idea. It's going to leave a nice impression on the board as it burns it. All right, so we go back to the project, double click on the painted object, and now we can set up the G-code job, GRBL laser as the preprocessor. The tool width we used is 0.75, so that's what we'll set. 1 degree angle for the V-tip, 650 for the XY feed rate, and we're burning quite hard on this, so 60% or 6,000 RPM in this case, and we'll generate the G-code. There we go. Now looking at the G-code job is quite useful as well because it includes the thickness of the tool, so you get a bit of an idea of what it's burning and what might not be burnt. For example, you see this little gap here, for example, but you know, that's not really a big issue. So save the code, save, project, and next up is actually an unnecessary step for this board. Let's just hide everything first. Save. We're going to create the mirrored side of the cutout for the PCB, as we said before. As I said, this is actually a circle, so you don't actually need to make it, but I'm going to make it just to make sure you know how to do it in case you do have that weird shaped PCB. So we need to reopen a new version of user 9. You'll see it creates a second version with this underbar 1. And we're actually going to mirror this file. So to get to the double-sided tool, we go Alt-D, we select that newly loaded file, underbar 1, calculate the bounds. Will it work? Oh yes, it worked this time. That's nice. So the mirror operation is going to be on the Y down the center, and we click mirror. It will mirror this, in this case, it's a circle, so you won't see it. But anyway, we've mirrored it. So anyway, you've seen how it works. Go back to the project, and now we create the additional job. Isolation routing, 0.1 we keep as is, and 22 passes, and 99.9999% overlap, so it's always burning the same spot. Generate the geometry, and we can go straight into creating the G-code job. GRBL laser, dip can stay the same, 1 degree angle, 650 speed, laser power, 100%, or 10K in this case. So that's everything. Create the CNC job, save the code, save, and that's it, right? We've got basically all the jobs now for created a asymmetrical single-sided PCB. But there's one more thing we've got to do, which is to create the job to cut out the stencil for laying down the solder paste. So let me just hide this again, disable plot, Control S. All right, so the solder paste, Gerb, is the F-paste. Unfortunately, I can't just use this Gerber file as is, because if I do an isolation routing around the edge here, I found that with these very tiny features, it will actually burn through these little joints here. I mean, if you're using large components, it's not an issue, but with this 0.2 millimeter spacing burning into paper, it's just enough to make it sort of burn through here. So we need to shrink all of these features down a little bit by a little amount. And this is basically the opposite of what we did with the copper layer, where we blew it up a little bit to compensate for the etchant in that case. So it's the same thing again, except we're doing the opposite. We'll go into the Gerber editor for this file, and we will select all of the elements. We'll use the buffer, and instead of having a positive buffer, we'll have a slightly negative buffer. It's only a little bit, just a little bit. minus 0.04. And if we zoom in and when I click it, you watch it, yeah, you see it. It is actually quite a notable change in the geometry there. So that's all we need to do. It modifies all of those pieces. We'll exit the editor, save the changes, and we can see the new Gerber object sitting on the top here. So the edit object is the one that's been selected here, so we can go straight on into the isolating routing. We don't need to do any painting, we just need to do a cutout, which is similar to the board cutout, but we only need to do one lap instead of multiple laps. So it's very similar in that regard, except we don't need any offset related to tool diameter, so I'm going to shrink the tool size to the smallest so it follows exactly on the line. We only need one pass, and the overlap obviously is irrelevant, but I set it to 0% in any case. Okay, so that's it. We can generate the geometry, and we can go straight into generating the CNC job. So set up the GRBL laser as a preprocessor. We may as well modify the tool size to 0.075. It's probably a little bit bigger, but that's fine. It doesn't work. Hey, 1 degree tip angle, 650 burn speed, and the power that I'm using is 3900 and 39% basically, and that's what I found is just enough to consistently burn through the label sheet that I'm using to create the stencil out of. Alright, so generate the CNC job, save the code, save. Yeah, that's pretty much it, right? I think we're all done. That's everything we need to make in here. Disable plot. Save it. And one thing you can do in here before you go and start trying to make the PCB is actually to have a look at some of these geometries and make sure they all fit together in the same plane and in a way that you expected. So what I often do is turn on the copper layer, I turn on the paint layer for the mask, and then we can see how the clearing pad operation sort of overlays with the etching operation, and then we can turn on the outline of the board, this paint, which is user 8. We can see how the edge resin will be cleared on the board in relation to the copper etching, which is really right on the edge, or just a little bit on the inside. And we can also see how or where the cut line will be relative to the outline and the area that will be etched to allow the cutting of the board to happen. So if we enable the plot here, we see that the cut line will occur here. We see that all this area here is cleared for the etch. And we see that the edge of the board's resin will be cleared pretty close right up to that cut line, well, close enough anyway. So we can see that everything looks nice, and you know, you can turn on a few of the other layers if you just want to be sure. For example, the Silkscreen layer, just sort of see how it all fits together, make sure it's geometrically correct, and obviously you can turn on the, well, that's the back side indicator, is it? Yeah, that's the wrong one. Let's turn on the front as well. Let's turn off the back. Yeah, you can just sort of take a look and just make sure everything looks right. And if it looks right here, it's going to be pretty much guaranteed to be right when you go to use the CNC job. So, you know, I think this is a good way just to check and just save yourself a bit of pain later on, that's for sure. Alright, so there's actually one more step we need to do before we can actually use these files. The way that FlatCAM exports GRBL laser files, there's quite a lot of junk in there. It's probably the easiest way to put it, I guess. So what I do is I go and just do a little bit of a cleanup operation to get rid of some of the junk. And I replace the header to make it a little bit more useful. Now you can actually probably do some of that work here using some of the features of FlatCAM, but I find it a bit confusing, and so I just prefer to do it in a text editor, and that's what we're going to do right now. I'm actually using Windows 11, which has a really nice text editor. So let's start having a look at these files that we created. We only need to do the modification to the laser jobs. The drill file CNC jobs, you don't need to touch them, they work just fine. So these alignment drills and the PCB drill holes, you don't need to make any modification to them. They're always going to work good. Alright, but we need to modify all the laser files, and you see there's a lot of them, so just open them up. And this is what I love about the Notepad editor in Windows 11, is that it has tabs now, and you can work very easily within all of those tabs. So if you're not using Windows 11, then that's a bit of a shame, because it's going to be a bit more painful. But anyway, it's the same thing. You just have to use multiple Notepad windows. So here I'm just opening up all these files. So what are we going to modify? Start with the copper one here. So the problems that I have is that all of this unnecessary garbage in here, these, for example, these G01 F60s is a Z-axis feed speed where there's no Z-axis move, so we don't need any of those. And there's this G01 F650 feed setting values, which are absolutely unnecessary because every single move has an F650 next to it anyway. So I just want to get rid of all that unnecessary garbage, just make the file as light and concise as possible. Likely it's probably not going to make a big difference, but I did have some issues with my old CNC where it would freeze up and have a hernia on the occasion, so I was always trying to make the files as light as possible. It's easy to do, it takes a few seconds, so I just always do it. So you go into Control F and replace, or Control H if you're in the old notepad. And you just want to put in the G01 space F66 extra, same as what you see here. And replace it with nothing. So replace all. And you want to do that for every single file. It's a shame it doesn't do it for all tabs, right? It only takes a second. And the other thing we want to get rid of is this G01 F650. Same thing, replace. All of the speeds are the same here, except for the Silkscreen layer. So we'll have to change it for that one here. So Silkscreen is 200, so we'll come back to that in a second. And then on Silkscreen, just grab that. Change all of those. All right, so we're done. And now I'm just going to add my custom header. So at the top here, it's pretty much the same. But below that, I just enforce the laser mode setting 32 to be 1. I also just make sure the rapids are set at the maximum possible speed. And I move the laser head up a little bit before moving it back to the origin point and then moving it back down to the 0 point. And then I leave a little user confirmation wait, which means that the user can then check the position is correct in relation to the board you're working with before you press the play button so that it continues on with the job. So it's just a little bit more comfortable and feels safer to have this header. So I'm just going to replace that in all of these. And now we just need to save all. This is a Japanese interface so you can't read it, but Control Alt S here, save all. We'll save all the tabs, and you'll see the little dots at the top here indicating that changes have been made and not saved. We save all, and they're all saved, and that's it. We are finally done, so we can just close that. And next up, we're actually going to finally get on with making the actual PCB, so that should be fun. Let's get on with it. Alright, so the first thing we're going to do is cut out this PCB, the size of which I've already determined by using KiCad to figure out how big it needs to be and how that relates to the size of the clamps that I'm going to use. In this case I'm going to use these smaller clamps which are going to go on either side like this, so as you can see the PCB is pretty small. So you want to get these edges as square as you can get them. Remove any top burr. So I think it's close enough. So this PCB is in pretty good condition, as you can see. There's not really any large scratches or really dark oxidization, so it's a pretty new piece of PCB. So I don't need to do much to clean it up. If it was really bad, I might go with a bit of Scotch-Brite first, just to sort of get it back to some decent shape, but in this case we don't need to do that. What we do need to do, however, is we need to polish it to a full shine. And this is a little bit different to what I've been showing in my earlier episodes, and this is a part of the new process. And getting this up to a full shine before we actually coat it with the UV resin will actually make the etching process much better. I found that the etching undermines less. And the second reason is that it makes clearing the pads or doing the final touch-up of the polishing the pads much easier to do if you pre-polish them at this stage. There is a little bit of a possible negative that I haven't fully characterized it yet, and that is that possibly by polishing it in advance might actually make the resin a little bit less likely to adhere to the surface. So in some circumstances you could actually peel it off. So it's good to have a little bit of double-sided tape on hand while you're doing this. And we're going to use it just to hold the PCB in place while we do the polishing. And I'm using KiCad, which is a Japanese brand, I guess. I think it's a Japanese brand. In Australia, I would always use Brasso when I was polishing boards. So I'm not sure what might be available in Europe or the US or Southeast Asia or Brazil or anywhere else. So when you're polishing the board, often you sort of miss the corners. So you really want to make sure you get the entire surface. I think that's looking pretty good. So So you're looking for a pretty consistent mirror finish throughout. So now might be a good time to don your gloves, I guess. We'll do a round of cleaning with alcohol. So I'm using this Silkscreen mesh, 150 mesh mono thread, and I don't know anything much about silk screening and I just chose this based on a little bit of research, but it seems to be doing the jobs. And I just use these little cut-offs for these smaller pieces. But what you'll find sometimes is that it's got like some deformities. I don't know if you can see it there on the edge where the string is pulling up, or it's got a fold in it. So maybe I'll just cut a bit off that edge just to try and settle it down a little bit. So for larger jobs, you might want to use a frame or something like that. But for these small jobs, I think it makes sense just to use this type of material and just use it once or a couple of times in one job and then throw it away instead of using IPA to clean it. Otherwise, you're going to waste a lot of IPA, which is probably more expensive than the Silkscreen. All right, I think we're about ready to go. Using this WNB series resin for this. And this seems to be working quite well. I've been using it for a while. I actually saw this stuff on sale on one of the other stores in AliExpress, and I left them a message asking them, is this real WNB product or is this a clone? And I asked two different stores and they both answered, oh, it's a clone. I'm thinking, okay, fine. At least they're honest, right? You've got to give them that. They're not all honest, but sometimes they are. So if you're a little bit suspicious with those stores, just always ask them the question, because they don't want you to receive the product and then return it because it's a clone. That's more hassle for them, so it's easy enough to ask them. It's funny when China is already cloning their own stuff. They don't care who they clone, they'll clone anything. So you see that I've put it on the board directly first, and I've always done this. I just really want to make sure that the resin is in contact with all the surface. Just hold down the end of the silkscreen with your fingers. Just keep going until you've covered the entire surface. Once you're done, you want to pick it off in one nice move, and that looks pretty good. And I recommend you cover it up pretty quickly, stop any dust getting on it. I'm going to reuse this later. I'm going to stick it and sandwich it in between a bit of clear plastic sheet, and then I'll stick it under something so it doesn't harden up, under a book or something. There's the other side, like that. And with any leftover resin, don't be shy, just scrape it back into the bottle. That's what I always do. It's never caused me a problem. Obviously, if it's really dirty for some reason, don't put it back in the bottle. So I'm just going to leave it for 2 minutes, and I do that so that the resin will flatten itself out. So when you use the silkscreen, there's also some degree of pattern with the silkscreen, obviously, the mesh, and you just want it to settle down and become quite flat. So I think we're 2 minutes up now. I'm actually just going to move it across to this board here. There's a little bit of resin I've touched on the edge there. I really should have moved it to this board first before putting the resin on there. You'll also notice there's a little bit of resin sort of piled up on the edges here. It doesn't really matter, so as long as the area of the board that you're going to work with is nice, that's all that really matters. So 30 minutes is how long we're going to expose for, so we'll just do that. Alright, so it looks like it's all done. A few little sort of dots on there. You always get a bit of that. The bit on the edge doesn't really matter, and where I touch it with my finger, so I think it's going to be okay. What we do want to make sure is that, see this resin on the edge of the board, that's going to mess with your locating. So what we're going to do is take the file and just make sure all of these edges, that they're square and they're clean. Yeah, it should be good. These are corner pieces from cutouts of some PCBs that I've made before, and I'm actually going to use that to secure the PCB in place. Secure it's probably not really the main point. The main point is to locate it, so as we remove the PCB and return it, it will always return back to the exact same position. So the inside edges of this have to be cleaned and filed, as do the surface of the PCBs. And we'll actually glue this onto the surface of the CNC's workbed. And I keep reusing these, so I mean I could just glue them on and use them once, but so that I can use them multiple times, I'm putting a bit of masking tape on the surface. So in this case, we're going to use a pretty tiny little PCB, so I ideally want to cover all four corners, but that's not going to be possible in this case. Instead, it's going to look a little bit something like this. We're going to have that little tiny PCB, these two holding brackets, and then we're just going to have one of these at the top to sort of hold it in place, and that's it. So it's only a 3-point location that I'm using in this case. As I said, I prefer to use 4, but it is what it is. So, put a bit of masking tape on all of these. Now we don't want any tape on the edge of the board that's going to interface with the PCB, because that will create some sort of chance for movement. We don't need that. So for those edges that will interface, I'm just going to chop off the masking tape. And for the remaining edges, I will fold them over so that the super glue doesn't get on them. You'll see that a little bit later. And so now we have that internal edge there for interfacing with the board. Alright. You'll notice that I've actually filled in all of the holes here with epoxy and then milled it flat. And that's the problem with this using the holes and locating pins, is that you end up really chewing up your working surface. So this new process for locating the PCBs is non-destructive. So hopefully if you're doing a lot of PCBs, it will definitely make your life a lot easier. Just cutting the tape where the screws have to go into those mounting holes. So I've got my little clamps here. Now you need to pay a little bit of attention of the location with relation to where you're going to flip it. Make sure you can mount it when you flip it. This is the top, bottom left, bottom right. So just make sure that your locating brackets are a nice tight fit. Obviously the top one here is not going to be anything but a connection there. I think that'll work well. Just going to use some accelerator and some super glue. So the trick here is you really want to apply a lot of pressure. And the lucky thing is I have this little hole from the original cut off piece, so I can use that to sort of wedge it in, but you really want to shove it in there as tight as you can. Put a good run of super glue along the edge. Then hit it with the accelerator. And hold it there just for a few minutes, or a few seconds anyway. Should do the trick. So I'll usually just leave it for a couple of minutes here to allow any of the super glue that the accelerator can't get to harden up a bit before I attempt to remove the board. Alright, so next step is pretty important, I think, is we have to remove it at least one time. Obviously we're going to clean off some of that accelerator and replace it. We just want to make sure that it's in a neutral position, that you placed it in and it's sitting in a very neutral position, not in any sort of a biased direction before we clamp it down. And obviously we want to make sure there's no movement, that your location guides are actually doing the job. And if your location guides are not working right, then obviously you're going to have to redo them. You can see the resin has cracked off a little bit here, where the clamp is pushed on that sort of raised bit. I think it's going to be okay. Sort of points to the fact that the polished part of the PCB also has a tendency to peel off a little bit more than the wire brush coated surface. But as I said, my experience so far is that it's not problematic in a real PCB, but just something to be aware of. Alright, let's put it in and see how it sits in there. You can see it sort of floats on the top there, so there's a bit of pressure. Just let it sort of go in. Just wiggle with your finger, make sure there's no play. I think it's going to be okay. Alright, so that's the PCB location guides done. Next up, we have to make a location reference. So the location reference, as I've designed it, has to be a minimum width of around about 10 millimeters by 40 millimeters of cut-off scrap with a resin coat. Now this again is a piece of the PCB that I have cut off, so I'm going to use that. So the holes obviously can't be used, so I'm going to cut it off, say around about there. I said minimum width of 10 millimeters, this is about 9 millimeters, so it's a bit on the edge, but I think it's going to be okay. Breaking my own rules, but that's okay, they're my rules, I can break them. The finish doesn't really matter, I'm just keeping it tidy, that's all. So this is a one-use item, so it's consumable, so it doesn't really matter. I'm not going to tape it on this side. Anyway, you'll see what I'm talking about. So we want to place the locating guide somewhat close to the PCB. Ideally, I'd probably want it around about here somewhere. So what I think I'll do, so just remove a little bit of this tape, just so I can get it nice and close. And we're going to super glue it on there. We need to protect the board. Hopefully that's going to be wide enough. So let's glue it somewhere over here, and we want it to be pretty square, try to make sure we get it in the middle of that tape and square. I think that'll do there. We want to glue all around the edges, pushing it down. I'll just hit that with the accelerator first. I think my tape was a bit too small. Anyway, just give that a quick wipe with some IPA. So I'm just going to home the CNC. Alright, so that's homing is now complete. And what I'll do is I'll just take the XY position here as 0 position using the homing sensors. So I'm not going to use my optical sensor this time. I'm just going to do what you would typically do. So set 0xy at this position, and that's just going to give us a reference as we work forward. And then I also want to set the laser height. Now I probably want to set it to this, but it's a little bit small and wobbly. Maybe I can do it. Oh yeah, we can do it. Let's just do it. Sometimes I do it on the main PCB, but we'll just do it on this for now. Actually, I changed my mind. I'm going to do it on the main PCB. Okay, so we've got the laser height set. Now we're going to set to this corner. Let's turn the laser on. Got your goggles on. Send it to the 0 height for the laser. Turn the laser on. Alright, so we're right on the corner there, I think. So we want to go 3 millimeters in. 1, 2, 3. And 3 millimeters up. Let's go 1 more millimeter right, just to make that laser in the center. So, okay, so before we set the 0 position, I'm just going to write down these coordinates. By writing down the coordinates, it should hopefully make it a little bit easier if we want to restore the position. It won't be perfect, but it'll get us in the ballpark, and that sort of speeds everything up a bit. So it's X 104 and Y 58. It's from home, right? So I'll put it on the page. I'll set the 0. And let's turn that laser off. The pattern that we're using is this one here. I'll show you on the screen. It's this cross that will be drawn first, and then it'll go up and it'll draw 4 sets of circles and a line. I think it's 8 times in total. And you can see the path is designed to remove any effects from play by zigzagging as it goes. So I'll see if I can make this available somewhere, or at least the specifications for the design, but it's pretty straightforward. Okay, so let's burn this. Okay, nice. Let's have a look at that. So you can see the center cross and then all of the positions here. I shouldn't have gone across that 1 extra millimeter. I should have kept it 3 millimeters, but that's okay. It's still going to do the job. Ideally, you want to have all of these in the center of the piece. Before we start actually burning into this board, we need to locate the laser in the right position. This is our 0 point, and we want to know the distance X and Y offset to the corner of the PCB. That's 36. That's off. That's 48. So 36 by 48. Okay, write that down. That's to the work. I think we can set 0. Turn that position laser off. Okay, so I've just got some cold water here for washing later on prepared. I have a larger IKEA dish here, which will be the bath for the boiling water, and the ferric chloride here, okay? So just pour that in there. So while we're actually burning the pattern into the PCB, this will warm up and then it'll be ready to go when we're all set up. Alright, so let's burn the pattern into the PCB. Turn the laser power back on, put the goggles back on. So what we're going to use is from the files that we made earlier. I've put them into a temporary folder on my server here, and we're going to use this pop-up layer one here. There it is, looking good. I'll press play. Alright, so it's all done. Let's take a look at what it looks like. So it looks pretty good. I don't think I see any issues. But it's at this point you want to have a bit of an inspection with your watch repair glasses. But I also have another little trick to show you, is that those magnifying watch repair kits come with a bunch of other lenses. So what I do is I take this 25 bi lens and I actually just tape it onto my smartphone, onto one of the lenses here. We just do that off camera. You've got to be real careful to make sure that the lens is centered to the camera's lens. You can also just use it in the zoomed out situation, like this, and you can see if the lens is centered or not. And there it is, nice and stuck in place with some masking tape. Alright, so what sort of result can we get with this? Look at that. So I'll take a couple of photos so you can check it out. It's nice to add a bit of extra light as well if you've got some, because it definitely makes the image look a lot clearer. So you get the idea, right? Your own digital microscope with a smartphone. Try not to put too much pressure on the alignment guides, you don't want to mess it up. Alright, so before we etch, I advise that you give it a bit of a rub with IPA. So this is where we want to make use of our fine toothbrush. You see the tips are very, very fine, and there are many of them. This is a very good toothbrush for doing this. So I'm just washing this in IPA to get rid of some of the black stuff, and it sort of builds up at different rates at different areas, and that sort of changes the rate of etching in different areas. And you really want to have a very, well, as much as possible, a very consistent rate of etching, otherwise you're at risk of undermining, which is really not good when you're dealing with tiny features. And as we've pre-polished the board, what I've found is that you actually get a much cleaner result after you clean it with the IPA here. Not too much pressure, otherwise you're going to damage it. Try to do it at a few different angles. You can clearly see where those two lines are separated and leave that sort of center line, but the resin's gone, you can see it's shiny. So to help with the etching, I'm actually going to use this little plastic spatula, and I want to sort of like wash the etchant over the PCB. So I'm going to stick it on there like that, and then we can have it as a handle so I don't have to stick my hands in the etchant all the time. That should do it. Okay, so let's etch this. So I usually get the brush and try to get it, make sure that the etchant is in contact with all the surface, so get rid of any remaining bubbles or surface tension issues. At least for the first 5 minutes, you don't need to be too stressed out about it. But after 5 minutes, assuming that your chloride is still pretty active, you should definitely take a look and check out how things are going. Not quite at the 5 minute mark yet. So we're already getting pretty far done. It's only about 6 minutes, pretty quick. There's just a little bit left on this top section here, so I'll just give that a bit of a focus scrub. Yeah, so it's cooking pretty good. I'll just give it just a few more seconds. Alright, so we just need to make sure that there's not anything left over. The great thing about these single-sided boards is you can use a light at the back, and actually that will quickly show up if anything's remaining on the board. On a double-sided board, it's going to be a lot more difficult. You can probably try to edge light it. I'm not sure how successful that might be. I haven't tried that. But I guess it would work to some degree, right? Anyway, let's take a look at it. We'll use the trusty tool here. And all those edges there look really quite good, right? So now let's backlight it. That etching is perfect. I was getting bad undermining before, and here it's basically none. Yeah, it looks really good. So what we're going to look for is just any remaining leftover copper on the board. I don't see any. This is only the second time I've used the pre-polishing method, and it's clearly much easier to etch and gives such a high quality result. So if there's any risk of like peeling of the UV resin, it doesn't happen when we're etching. I mean, I'm scrubbing that with a brush, and you would expect that if there was going to be some sort of easy peeling because of the polishing, that these tiny 0.1mm or 0.13mm etching paths would peel off, right? But it doesn't. Yeah, very damn impressive, that's for sure. All right, moving on. So the final step of the etching process, we'll just pop it off here. Let me go run that under some water quickly. So it seems there's less of a likely it's going to be a problem with this new pre-polished board, but historically there's always been a little bit of etching that gets under the undermining parts. Regardless, before we move on to the next step, I always like to hit it with a bit of IPA just to make sure that we're nice and clean and free of all of that etching. I just rotate it at 45 degrees intervals and give it a scrub. Got the glove on the wrong hand, look at that. Okay, I think we're done. And let's stick this down on here. If you can find some double-sided tape with a weaker adhesive, I reckon that would be a better way to go, but anyway, there we go. So this is a bit tricky because there's all these tiny little gaps in here and everything, and what I find is there's always going to be a few air bubbles remaining. So if you look at it with a backlight, you can see those air bubbles that remain in the surface. So I try to minimize them as much as possible, but yeah, you're always going to get a few bubbles in there. But even though there are air bubbles that you can see when you backlight it, when you normally look at it, you can't see the little bubbles. They're not noticeable, so it doesn't really matter, but you know, it's all about OCD and being detail orientated as I am, so let's get it right. So, same thing. Try and push it right into all those little gaps from all the different angles. I really don't want to have any getting on the edge here, so I'm just going to knock that off. If you get it on the edge, it's going to mess up the alignment. So fiddle around with it as much as you like. So now I'm going to pull out this silk screen that we used earlier and reuse it. If you're doing multiple PCBs, there's no reason you couldn't just keep reusing this silk screen for your session, that's for sure. But we're only making one PCB here today, so let's get my big spatula. See if we can get it right. Let's do it. Do a visual check. Looks good. Cover it up as quickly as you can. Give it a couple of minutes to settle. Okay, should be enough. Oh. So it looks like we're all done. Let's turn this off. Yeah, I think that looks pretty good. So now we're going to do the silk screen coating. I'm going to preheat my little hot plate here to 80 degrees because we're going to need that in a second. And the first step is cleaning, IPA again, because there can be like some sort of residue that can affect the quality of the adhesion of the next layer. Well, I think there is, because I found that cleaning it seems to improve the degree of adhesion. So this is the resin that I'm using, this mechanic stuff here. And it sets up a lot quicker than the WNB stuff. And I'm just going to turn the light off a little bit. I don't want too much light while I'm doing this. You don't need a lot, just enough. It's probably too much, but anyway. So, same with any of these resins, I recommend trying to force it into the surface. And this also has some sort of like oily substance in it. Sometimes you can see it, it's like clear and it separates. So I recommend really mixing it up and spreading it around over all the surface where you want the silkscreen to be apparent. Make sure you get all of the things near the edges. Alright, I think we're looking pretty good. And let's get a piece of silkscreen. Nice and smooth removal. And there you have it. Alright, let's see if I can get it off there without making a mess of it. Should be able to. The problem is going to be the double-sided tape is going to be left behind underneath there. So now we're going to stick it on the hot plate here, and we're going to stick it on there for exactly 10 minutes. Take note of the time, stick it in the middle of the hot plate. Alright, so we're coming up on 10th minute now, so I'm just going to get ready and we're going to drop the temperature down to 50 degrees and cool it all down a little bit. Alright, so I'll just let that cool down. So while we're waiting, I'll just load up that file that we're going to need. File open. And we're going to have the Silkscreen. Alright, there it is. Okay, seems like we're cooled down enough. Should be able to pop that off there. Just be careful to pop it in here without disturbing the resin. Okay, let's turn the laser on, laser goggles on, and let's run this program. Okay, we're all done. Right, let's get it off the CNC and see if we've got anything to look at. So what we're going to do is we're going to soak a tissue in IPA. You wouldn't believe it, would you? Unless you saw it with your own two eyes. You can only get so much off doing it with the tissue. So just use one tissue to get rid of the bulk of it and then switch to brushing. And you should be, you know, I feel pretty gutless when I'm doing this. I always don't want to brush too hard because I think I'm going to rub it off. But in theory, it's either wrong or it's right. And in this case, it looks like it's wrong, which sort of sucks. And there you go. It was wrong. Why was it wrong? Alright, I'm bringing you back after half a day or so because I actually ran into a bit of trouble. Let me explain. I've done maybe more than 10 different times I've actually printed this out and got pretty much the perfect result. And this is obviously some of the development areas. But once it's right, it was staying right. However, when I did it this time, which is quite a while since I'd done a print, for some reason it just wouldn't stick, and I just kept testing all different types of things to try to solve the problem. But in the end of the day, it appears that it was simply just a lack of power. So when you wash this with alcohol in the final wash, it just should not come off. And if you scrub it and it starts to come off, then it's just not right. Your power level's not right, or something else is wrong with your process. But you can see clearly that scrubbing it clean means it does not come off. So it's a bit frustrating. So what's going on here? Why have I got this change in what has been a pretty stable process? Well, there's only one of two things I can think of. One is that I have had some sort of change in the amount of power I'm getting out of the laser for the setting that I'm providing, even though I'm using the same setting. The other thing it might actually be, and I think this is quite a reality, is that the resin that I'm using, this mechanic resin, and I'm using it because it sets up very quickly compared to WMB. If I tried to use WMB, it will never work. So this mechanic resin that I'm using is in this syringe towel shape. And if I look inside here, for example, I always notice that there's always a little bit of separation that occurs over time. So I usually stir up this WMB stuff to get it all mixed up. There's not really any stirring up this. So what I think is happening with these is some sort of degradation of the product over time, and it varies in the position of the tube depending on the storage orientation. And that sort of makes sense because when I've squeezed it out in the past, sometimes I get a lot of clear liquid that sort of settles on top, and right now I'm not really getting much at all. So I expect there's something to do with the effective mix that I'm getting at the specific point in the tube that's affecting the amount of power that I need to get it to set up. I'd actually nearly given up, and I've already got some of this on order, some new stuff. At least, you know, if I have the problem, it means that you will have the chance to understand the problem should you run into it too. It is a little bit of a fickle process, but as I said, once it's right, it stays right. I think that's really the key thing, and even I doubt myself when I'm doing this because all of a sudden it doesn't work, and somehow I just forget that it will work. But it will work, and once it works, as you saw, you can scrub it really hard and it won't come off. I was getting a bit aggressive with the laser setting, and I actually have increased it from the original 4.7% setting up to 6.7% now, which is a pretty large adjustment for this, considering that I normally had been adjusting it in changes of 0.1% of power to affect notable sort of adhesion differences. So yeah, that was quite a long way difference. So right now I think I'm a little bit hot, but even so, it's still a pretty good result. So after you've got it clean, I'd still recommend sticking it in the UV exposure. This stuff sets so quick, so you don't need long. So I'm just going to put 30 seconds. And that should just help lock it in. So let's talk about the process a little bit about what I've done. So the cleaning that you saw me doing before I apply the resin, that's just to make sure there's no residue. And then the application, making sure the application is thin and even, is just so you get exposure consistency. And then there's a heating aspect of it. And the key reason for baking is just to get a much more crisp result. Because if you don't bake it, then as far as I understand, those clear liquids will, after the first resin is hit with the laser and hardens up, it will then bleed the light to other areas and create that very sort of blurry and rough edges on the result. So yeah, I think that's about it. As I said, this is not one of my best ones, but I'll show you what it looks like under the microscope camera thingy. Oh, and by the way, the idea of baking the resin to get a better result was stimulated by a user's comment. He had indicated that he was getting very good results by baking it. So his results and my results are very, very different. But what I did find out by attempting what he had suggested is that the quality of the Silkscreen design was much, much cleaner, significantly cleaner. And that was really a key piece to the puzzle. So even though, what we're seeing in our applications being quite different, his comment effectively led me to the solution, which, so yeah, a big thanks to him and to anyone who really leaves those comments. Sometimes they really do make all the difference. So yeah, keep leaving your comments, that's for sure. Okay, so moving on. First up, we're going to load the file for clearing the pads. Which one is it? Mask. Okay, we're all loaded up there. So I'm actually using Air Assist, and you'll see the Air Assist nozzle there. That is actually something I've made myself. I didn't make a video on it, unfortunately. And the hose just goes up and around and down to the bottom there. And then I've got it running into a thicker hose, which comes down, and I've made this other fitting that plugs it into my compressor here. Now it's a pretty big compressor because I used it when I was building my house, so I don't think you need something this big. Yeah, but there is quite a bit of air usage in a single job, so whatever you can get is what you can use. Any air assist is going to be better than no air assist in this specific job. So I put the board back in there. For the Silkscreen, I managed to pull this in and out of here a good 10 times. It's probably loosened this up a little bit more than it should be, which is a shame. So we might see a result which is not so perfect, but hopefully it'll be good enough to be able to complete the PCB. Otherwise, I'm going to be making the video again. Let's get my compressor going here. And I want a good amount of air flowing, so I'll give you a listen to what that sounds like. Okay, see how we've done here. So the alignment looks like it might be okay. Size is good, right? So that's what it should look like. And as you can see, the Air Assist does a great job of ensuring that we don't burn any of those smaller pads. And that was something that I struggled with a lot in those earlier videos that I'd showed. So let me just explain quickly for those who haven't been watching about what the problem is with clearing these pads. If you've got very tiny pads with no real connections to like big thick tracks coming off or anything like that, then they have very poor natural ability to dissipate heat. And so when you shoot them with a laser for any period of time, they will build up the heat very quickly compared to pads that can sink a lot of heat. And once they get up to a high temperature, they will actually start burning the substrate underneath the copper, and then they'll fall off the board. And so that's obviously not something you want to have with a PCB. Alternatively, if you use a power level which is very low to clear those types of pads, that's not going to be adequate to clear other pads that do have a good sinking ability, because they will sink too much heat and there won't be the ability to build up enough heat to clear the resin. So it's been quite a dilemma, and it sort of occurred to me that using Air Assist is probably the better way to go, that you'd be able to cool the pads proactively and therefore flatten out the cooling level on all of the different pads and use one power level. And that's actually what I've come up with here. Now, if you don't have Air Assist, you can still clear the pads. It's not impossible, but it is a little bit more fiddly. And what you need to do is you need to, once you import the mask into FlatCAM, you'll need to edit it and divide it up into maybe 2, 3, or even 4 files and create different jobs for each of the different pad types. And what I mean by pad types is different degrees that you believe that these pads might be able to dissipate the heat. And it's a bit of something you need to get used to, and you'll have to figure it out. So in this case, you can see that I'm using power levels of 4400 and I'm not burning the substrate. And 4400 even on those tiny pads, which is pretty crazy to me. And we're actually clearing the etching layer at 5000 or 50% power levels. So it's very, very close to that. So I think at the 4400 with the Air Assist, you would probably be able to clear just about any type of pad. So you might be able to say that without Air Assist, the biggest pads probably could still be cleared with 4400 or 44%. And maybe the smallest pads, I don't know, maybe you would have to go down to around about 25%, 2500 or 3000. All right, so the next two jobs are pretty straightforward. We're going to clear the resin around the edge of the board, and then we're going to cut the board, and we may as well do that all in one job. Air assist I don't use for any of these jobs because the sound of the compressor is really annoying. So I thought it might be beneficial to use air assist on some of these different types of jobs. But my final conclusion was that only clearing the pads requires you to use air assist. The other jobs, you just don't need it. It's not necessary. It doesn't bring any benefit. And obviously it's causing wear and tear on your compressor as well as to your ears. Yeah, it's pretty annoying to hear that compressor. All right, so let's just run those two jobs. I'll load the first one. The file, open, and user H should be the one. We'll just run that straight away. I don't have a cover over this while I'm working, but I do have an air extraction fan over here to the right. There's my air extraction fan. So it's not ideal, but obviously I'm filming it, so this is for you guys. If you're doing this work, definitely have the appropriate cover over your machine while you're doing it, and ventilate it outside so you're not gassing yourself. All right, let's run it. I'll turn the laser on, get my goggles on, and go. Alright, that was pretty quick. Let's take a quick look at it. Just clearing that 1mm line around the edge of the pad. And I'll also just grab a couple of photos of that for you. So the next job is the burn job. We just load that up here. So there's two of these 9 jobs. That's for the back side, the GBR underbar 1. So this is for the front side, user 9. And you can see it's just going to go around in circles and burn. So I'm actually going to leave the room while it's doing this, but I'll try and get it in a position where you can watch it while it does the job, because this really stinks. So at this stage we've pretty much completed all the laser operations for this side of the board. And you'll notice that this looks pretty nasty and it probably seems pretty concerning, but actually this is fine. This is perfectly fine. This will all clean off. And if you use air assist, it actually is cleaner, but it's pointless because it's the same quality result after you clean it up anyway. So as I said, no point using air assist. Let's get it off there and clean it up and then take another look at it. Let's see what this looks like. So we're not trying to fully clean the pads or anything here at this stage. Just get them roughly clean, even though they look really good. And that's all because we're pre-polishing it. With any luck, I haven't shifted the position. I'm a little bit nervous about this QFN package. Oh well, if I've messed it up, I've messed it up. Good enough for now. We'll be doing some more cleanup later. So I think those QFN pads are there, okay. So I think we're going to be okay, and you can see how good those pads look. It's insane, right? As they say in Japan, pika pika, which is probably where the word pikal comes from, right? Pika, pika pika. Beautiful. Yeah, it looks like we got the QFN pad. It's okay. It looks a little bit of alignment error, tiny bit, but I think it's well within, well, pretty close to being perfect actually, so I think give it a big pass. Alright, so I've got that spindle installed there now. So the first thing we need to do is home the CNC. So it's home, so now we're going to set the XY0, and now on the console I'm going to type these coordinates. Let's go. Okay, I'm just going to set to 0 there for now. And before we move on, I want to install the 1mm drill. So this is the vac stuff that I'm using. I really like these. And you can see I've already broken a couple of them because of my original testing. And we want to set the height. This is where you're going to smash your drill bit. There we go. So now let's go to G0Z0.3. Okay, what we have to try to do here is get the center of the tip of this drill to be at the center of the cross on the aligning thing. It doesn't matter if it's not perfect, but you want to get it as close as you can, so you've got to do it by eye. Alright, so I've got it pretty close there. I did forget to mention, the first thing you can do is press the go to XY0, and that's going to get you pretty close, and then you can just do fine 0.1 or 0.01mm adjustments until you're over the center. And in this case, I was only 0.2mm off in either distance by reusing this original figure that I had here as well. So it's pretty close. So once we've shifted to be above the cross here, you want to set XY0 again. And now you want to go to millimeter movement and move 4mm that way. 1, 2, 3, 4. And that should put you right over the first little circle. Set the XY to 0. So then I'm going to load a little program to drill those 4 holes, and you can see it's using that zigzag pattern again to get rid of any effect that the plane might have. Okay, let me move the spindle up. Now this job only drills down around about 1.4 millimeters, so it doesn't drill all the way through the board, and that's because I don't want to damage my waste board. Anyway, let's stop talking, let's see if we can make it work. Let's take a look at it, see how we did. So you can just see what it's done there. Made those 4 little holes there. So now I'm going to use my tricky little tool and we can figure out how much adjustment we need to get it center. And actually I got it pretty close, so it's a bit of a rare occasion. But you just got to remember that the outside is laser burnt at 1.2 millimeters and the inside drill hole is 1 millimeter. So in theory the difference should be exactly 0.1 millimeters. Assuming you're inside the circle, you shouldn't be making any adjustment larger than 0.1 millimeters. So what do you say, folks? Go up by 0.5 and go right by, I don't know, we can just try 0.5 for the moment and see how we go. See, if you overshoot, you can always go back, so it doesn't matter. So I've made the adjustment to the origin and I'm going to set XY to 0. Now go back to the 1 millimeter movements and we're going to move 4 millimeters up to the next section. 1, 2, 3, 4. Set XY 0 again, and we should be able to run it again. You can just see straight away that it's totally far off. I made 0.4 millimeter adjustment where I should be making a 0.04 millimeter adjustment, and that's okay. Go to XY 0 again. So we'll take that error out. Down 0.4, 1, 2, 3, 4. Left 0.4, 1, 2, 3, 4. So set XY 0. And let's go back to 0.01 millimeter adjustments. Up 4, 1, 2, 3, 4. Right 4, 1, 2, 3, 4. Set XY 0. And 4 millimeters up. 1, 2, 3, 4. Set XY 0. I think we can say that we've probably overshot a little bit. How about 0.01 down and 0.02 left? Now, I know this process looks like it's taking a long time. It's because I'm filming it and I'm messing around and I'm thinking about what film and I'm thinking about what I'm doing. If I'm actually doing it, it doesn't take very long at all. You just sort of go and you're pretty much done. So that's the final one there. You can see that there's a bit of movement in the system anyway, and there's a lot of burring on this drill. So if anything, I'd say this drill is a little bit blunt, not ideal. Even so, if you look at the top ones here, they look like they're pretty close. Could go to the left just a little bit. I think the height looks about right. Yeah, I think you're pretty much as close as you want to be, I think, with that. So I don't think this is the best job I've ever done at doing this because, as I said, I'm filming it and whatever. For me, I'm going to live with this as it is for now. So the next step is we need to go to 0 again. And let's go to the 0.3 millimeter height on the Z-axis. And the next thing we want to do is in 1 millimeter intervals, move back to this origin point. So now we are precisely aligned over the top of the origin point of the reference marker. Set XY0 and let's move the drill up out of the way. And now we want to go to this origin. Now before I set the 0, I'm just going to slowly drop the Z and we should be right on that corner. Just quickly eyeball it. So set XY0. So after all that work, we now have the drill aligned perfectly with the PCB. So for the next part of the operation, we're going to do some drilling. You've probably seen it before, but when I've been drilling, typically I'm drilling into the wasteboard, but as you drill, you get more and more holes and that destroys the wasteboard. So instead, I'm actually putting 2 layers of this plastic sheet, which is just from our clear folder. And then when I'm drill, I'm only going to be drilling into that plastic sheet. So here's one that I've used before. You can see it's got the holes in it. And it's just one use, but you know, it's just a consumable is the way you got to think of it. Okay, let's make that. Okay, got everything set up now. The waste sheet in, PCB in. So before you drill the holes, you need to probe the height. So you're not drilling beyond those packing sheets that we've got in there. Have I got everything connected up? Yes, I have. Probe. Okay, so now we've got the correct height. So the file we want to load is the alignment drills, not the conv edit ISO. That's the laser burn that we're going to need a little bit later. So this one here, the alignment drills, should be ready to go. Go for it. Oh, that's so close to the brackets. Oh god. Lucky I laid that out in KiCad first, otherwise I'd be smashing those in there. So next up, I'm going to load the plated Thru-Holes file, PTH file. It's just 6 holes that I've got for the header pins. Let's see what it does. I'm not feeling very confident about that, but anyway. This is going to be quite a bit off. It's a bit of a shame, but so that's literally the worst that I've done in ages. But it doesn't mean that the process is wrong. It just means you need to be careful when you do it. I mean, you get the idea of the process, and that's what I'm trying to show here. But this is just a blunt drill. Even so, they're far from unusable, so it's okay. It's a pass. I'd call it about a D. And yeah, as I said, it's literally one of the worst ones I've done in a while. Anyway, it is what it is. We'll move on. Okay, so we're back in with the laser installed now. First thing we want to do is go home. Now we're going to set XY0, and now we're going to go to these coordinates and set our XY0. And now we need to set the height of the laser. So we'll take the height of the alignment marker. Okay, we're looking good. Go to XY0, go to Z0, get your laser on, get your laser goggles on, and turn on your position laser. You need to check the best you can that that laser is going to be over that XY position. So I think it should be okay. So let's turn the laser off. Let's move 4 millimeters up. 1, 2, 3, 4. Now we're going to be over one of those holes that we drilled. Yeah, I can see it's lighting up that hole there, so it's going to be okay. Laser off. Set XY0, and I'm going to load a laser alignment file. Drills those 4 holes with the little movements to get rid of any play. So let's just run that and have a look at it. Go. See how we did? Yeah, we're a little bit to the left. We're a little bit to the right, sorry. We're a bit too far out to make a good judgment. So I think I'll come back to the left, 0.1 and up 0.5, okay? We're going to go to XY0. So we're back at 0, we're going to go left by 0.1, smaller, and we want to go up 0.05. Set XY0, 4 mils up, 1, 2, 3, 4. Set XY0, and run it again. So now it looks like we're much more in the ballpark. So the distance between the two should be 0.1 millimeters, and we can see that on the left-hand side, we're nearly overrunning it. So maybe it's 0.8, so maybe we need to go 0.4 to the left. And I'd say the bottom looks pretty close to be the same too. So what do we say, folks? 0.03 left and 0.03 up. So yeah, that's looking pretty close. Not sure if I want to play with that at all. Okay, for this demo I'm going to call that good. I have a whole lot more places I could test up here, but I don't need to. I'm pretty sure that's looking as good as it needs to be. So we go back to XY0 and position laser on, and now we want to have 1 millimeter movements until we get back to that spot, which is probably 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. Yep, we're there. So set XY0, and now I'm going to go the X36 Y48, and now we can set the XY0, and yeah, I can see it's right on the corner of that PCB, so just getting some confidence. Let's turn the laser off. Okay, so what I want to do is get rid of that packing, because we're going to burn a laser mark onto the masking tape that we have underneath, and that's going to help us with flipping the PCB. So get rid of that. The one thing we do need to do is that if you look at these locating holes, they usually have a burr on them. Actually, they look pretty clean. You can sort of see that the resin is picked up. I mean, if they're clean, that's fine. Oh, interesting. Okay, just make sure the holes are clear. If they're not clear, then just use a 3mm or 4mm drill just to quickly just touch off and knock the burr off. But I think that's not going to be a problem, so we can just leave that as is. And we've got that packing out now, so we're going to mount this back into place, even though it's a bit loosey-goosey. So now we need to set the laser height to be the surface of this tape. Let's just get the laser close by. So we want to burn onto this surface, so we need to set the laser height to be that. Close enough. Probe the laser. Okay. So now we're going to open the job to drill those marks inside those holes, which is this one here. You can see the job there, just small little circles. Let's start the job. Go. Alright, let's see if we've got any marks in those holes. How can it be that far off? Wow, that's just miles off. I figured it out. I put the PCB in upside down. See, I'm getting tired, end of the day. I'm thinking, well, how can they be that far off? Doesn't make any sense. Everything's recoverable so far, so it's a good thing, right? I think there's pretty good recoverability in this process in general. I mean, you can usually pick up on it and fix something if it's wrong. Let's pop it off and have a look. See if we've got those marks. We'll see if I've still failed. Anything is possible. I think we've got them. I think you'll be able to see them. Let's see if we can get one of them on the camera here. There it is. A little laser mark inside the hole. Perfect. So I'll actually use these glasses to align it when I flip it with those holes. Well, you'll see in a minute anyway. Let's get rid of these clamps. And we don't need these location guides anymore, so we'll just get rid of those. Just be careful not to disturb your markers, your laser markers, otherwise you'll have lost everything. Alright, there we go. So I'm going to do this off camera because it's just going to be sticking my head in the shot. I know it sounds like it's difficult. It's actually really quite easy to align. You can just sort of look at it from above and then sort of line it up and then get it to the holes, and then use these glasses just to look down the hole and make sure that all four are lined up. And if they are, you can clamp it in place, maybe tap it a bit to get it in the right location, and then you're done. So just let me do that off camera and I'll bring you back. Anyway, that's gone well. So I've clamped it down nice and firmly there and we're ready to go. Obviously, one thing we need to do before we go to the next step is probe the height of the PCB. Now we don't have the locating guides in the way here in this case, so thankfully we can just do it directly on the PCB here. So let's just do that. Be good there. Lower it a bit closer. Better not forget the alligator clip. Alright, so we're all set up and we're ready to go on with the next step. Alright, since this is not a double-sided board, it's pretty simple what we need to do as far as the laser work goes on this side. All we need to do is burn in the PCB markings and cut out the board. So we're going to do that all in this one big step. So first up we need to load the file. So file, open, and we want the backside silkscreen, which is not a silkscreen, but you get the idea. So that's nicely loaded there. Alright, let's get to it. Okay, so turn the laser on and let's go. Okay, now we can go straight to loading the operation for the cutting of the backside of the board. Now, as you know, I made a separate file for the back side, pretending that it's not a symmetrical board. Obviously, we would normally just use this user 9 file here, but we're going to use this user 9 underbar 1 file in this case. And yes, it looks exactly the same, but that's what we're going to use. The one difference that can be noted, however, is that it's actually starting from the right-hand side, whereas the other side was actually starting from the left-hand side, which is sort of interesting, but yeah, that's an indication that it's actually flipped. So I hit the play button and go. So that's managed to stink up the room a bit, but looks like we're all done. Let me just get this out of the way. So just as with the front side, you can see it looks pretty nasty straight off the laser. I'll actually give you a bit of a look at some close-up images here. But let's get it off the laser and give it a hit with some IPA. So you'll notice that these holes are a little bit off center. This is actually not the board that we're making. This is actually a reshoot of the footage because I managed to forget to press the record button. So I used this bit of scrap to simulate the operation, but it's the same thing anyway. You can see it's not the real thing. Anyway, the close-up images which I'm showing you here are from the actual board, and this is what it looks like. Yeah, so it's not a difficult step, and we're all done. So let's go on to the next one. Okay, so for this next step, we're going to be making the stencil for the silkscreen. So let's just take all this stuff off here first. We don't need this anymore. So as we're cutting into paper, it makes it a little bit tricky because we don't want to really create too much burn. Otherwise, it will actually make the burn path too wide and send things out of tolerance. So what I have come up with is using a piece of blank PCB as a heat sink. It will suck away the heat immediately after burning the paper, so that should close down that burning process, and it does seem to do that. So it also protects your baseboard from being burnt unnecessarily. So what we're going to be used to create the stencil is this laser printer labeling paper. Looks like it's meant for printing labels on wine bottles or something like that, but it just says specifically for laser printers. It comes in these big A4 sheets. I'm sure you'll find something similar. It's sort of like got a glossy, somewhat plasticized finish, and I guess that's intended to work with a laser printer. And we're actually going to need 2 layers of it to get the correct thickness for the paste. So I've already cut out 2 pieces here, but instead of sticking it directly on here, what I actually do is we're going to lay down a piece of masking tape, which is just hopefully wide enough. And then we're going to stick down the first layer. Make sure it has no air bubbles, get it nice and flat. So we're only going to be burning 1 layer at a time. If we try to burn through 2 layers, then we need more power, and more power means more fire. Basically, it's going to make the gaps too big. So we'll do the 1 layer first. So there's one problem that I found with using this specific type of paper, and maybe I chose the wrong thing. Maybe you'll find something better, I don't know. But because of this sort of glossy semi-translucent finish, sometimes the laser just doesn't initiate the burn in some sections of the print. So it actually skips over it. And that's quite a pain in the bum. So I found out a way to solve that, and that's just to take a little bit of Scotch-Brite and just to knock down or dull down all of that glossiness. So we'll just do this very lightly. Just make sure there's no glossiness left on the surface. Wire brush finish is fine. That looks pretty good. And I'll just hit it with a touch of IPA just to get rid of the dust that I've generated. So for whatever reason, I've actually had the CNC shut down between steps because maintaining the origin for the PCB work and the silkscreen is quite irrelevant. So I'm just going to home everything here. Okay, let's set the height. Let's probe it. Let's just turn that laser on and try to position it roughly to the corner. And I've got the PCB here, so why don't we, I've never done this before, but I think it's a good idea. I'll try something new on camera for the first time. We know that all the jobs are going to be aligned roughly to the same place of the corner of this PCB. So if we put the PCB on there, make sure it's sort of somewhat centered to the sheet. Doesn't need to be so perfect. Now I'll turn the laser on. Got it. Oh, I'm pretty close straight away. To do, set XY0. Laser off. So we're just about ready to go here. Now we just need to load the job. File, open, and we're going to have the paste one, right? Something like that. Hopefully that's going to do the job. Okay, so I think we're ready to go. Let's cut this first layer. Move the laser out of the way and do a bit of an inspection. Yeah, it looks like we haven't missed anything. So there's a few furries there that we'll probably just knock down with a tissue here in a second. You'll also notice that the QFN package slots are very tiny. In fact, there's nothing left. And that's really the tricky bit, right? Even though we can burn into the resin quite precisely the shape of those pads, in paper it just blows it away. And that's why I go to all this hassle of having this copper plate. So just knock down, hopefully into that garbage. And lay down your next layer, hopefully with no air bubbles. And same thing again, hit it with the Scotch-Brite. And run it one more time. Don't need to do a height readjustment or anything like that. Obviously there's very little difference in the height there. It's going to do the job. And that's it. Now if you're finding that it's getting burnt too hard, then obviously drop your power level a little bit. That's going to help you solve the problem, I'm sure. Let's do one quick clean. Remove off any nasties. That's what it looks like. Don't use a tissue when you're cleaning this. Try to stick to using a fibre-free cloth. Yeah, it's not so great, is it? I knocked one of those QFN legs off. I will change my setting a little bit to drop down that power level next time. It's just a little bit too hot, isn't it? So, let's remove it. Alright, so there it is. So there's one more step which I found necessary to do when dealing with this, is that the sticky side of this can be just too sticky sometimes. So what I will do is I'll get rid of some of the stickiness by putting my human skin on it. You don't want to be too aggressive. Just keep going until you feel that most of the stickiness is gone to a very light level remaining. Alright, and we don't want to get any dust in it, so you need to put it somewhere. So if you've got a clear plastic sheet or something, put it on there, but I'm just going to stick it on this edge here with the corner sticking out to make it easier to peel off. And I'll give you a quick look at the remains. All of the cutout pads should remain behind if you've got the cut correct. Now if you've underpowered it, then you might have a problem. But doing it this way with the masking tape, I found that the removal is very good for all of the pads and the process works pretty good. So yeah, if you think it's good, give it a like. I don't care if you give it a like or not really. Don't give it a thumbs down. That's the way to go, guys. So in this section, we're going to discuss about how to prepare these pads so they can take the solder paste and do the soldering job. Now you might think this is a pretty straightforward thing to do, but I can assure you it's definitely not, as can be seen by all of these tests that I've done here. And this problem has been with me since I started developing this process actually, and you'll see it in some of my earlier videos. Even the simple single-sided through-hole board had a problem with trying to solder. I really had to scrub and spend a lot of time applying heat before the solder would take up and solder to the pads and the wires. So clearly I knew there was something not quite right after clearing these pads. And I even made a post, I know I sent a post out showing a photo, I think of maybe these boards here, saying that I'd managed to clear the pads quite well and it looks good. But even then, when I did the test, I found out that they wouldn't take up solder at all. I even went and polished them like I'd done in my earlier episodes. I tried etching and etching destroyed the pads. So everything was a bit of a disaster, to be honest. It didn't look like it was going to work out. So I decided to be a bit more scientific about it, which is sort of rare for me. I'm usually just shotgunning at this stuff. But it's such a difficult problem to solve that that's what it required. So after a little bit of analysis, I had discovered that these pads actually weren't being cleared enough. Even though they look quite shiny, they still had a very thin layer of resin on there, which was quite difficult to remove with polish. So clearly I wasn't applying enough power to remove enough resin. In my earlier videos, I could use the polish relatively easy enough, and that is just effectively scrubbing off that remaining resin and polishing up the surface to get it to position to take solder. But it was never really all that successful. There was always a little bit of poor take up in some areas, so I wasn't very happy with that process either. So let's talk about the problems, all right, so you can have them in mind when doing them. The first problem is are you clearing enough of the resin. You need to find the optimum point where you're clearing enough resin. Any resin is going to be there, obviously it's not going to take solder. And there's another issue you need to consider, and that is oxidization. That's something that is difficult to solder to. It's not impossible. Things like flux, etc. will help you solder to it. But when we're talking about solder paste, we want that to be fairly automatic. We want it to heat up and then take up directly into those pads immediately. And quite often, just flux alone without agitation isn't going to allow those pads to take up the solder. So when it comes to oxidation, there's really two things you want to think about. One thing is you want to minimize it. And once you've minimized it, you have also the ability to polish it to try to get rid of any remaining oxidization. And I think there was one issue which I didn't fully understand, is that when I'm wire brushing before I coat it with the resin, it actually creates a rough surface. And when you think about it, it's pretty obvious. A rough surface like this with the solder paste, which turns into a liquid on top, the surface tension of the solder paste actually doesn't really want to get into those little gaps, and it will actually ride on top of all of those little ridges that you've made. So it sort of dawned on me at some point that that could be the problem. And I did some tests with some small pieces of wire brush and polished surface, and clearly the wire brush would take up the solder paste to some degree, but the polished surface would take it up immediately. So having a smooth polished surface is what it's all about. So the next step I did was to go through and try to figure out the best power level for the laser. And I ran it from 32% up to 52%. And 52% is beyond the power level that I use for clearing the resin for the etch resist pattern. So that's pretty hot. And unsurprisingly, at this level, it literally just burnt the pads right off. So those QFN pads there have just been destroyed. I'm not sure if you can see it on the camera there. The heat also changes the color of pads a little bit. The hotter it is, they start to get a little bit darker at some point. That's because, as per what I saw in a recent breaking taps video, the way to create oxidization to accelerate in a copper surface is to apply heat. So obviously applying a lot of pinpoint laser heat can cause and will cause oxidization. So that's obviously not going to be beneficial to getting the solder to take up. And obviously at the other end of the scale here, we're just not clearing the resin, so even though they look sort of shiny-ish, they actually have a thin layer of resin left. So what I did to try to decide what to use was to look for which of the pads had the most brilliant shine. I know that seems like a weird thing to say, but so the idea behind that is that the shiniest pads or the brightest pads are the ones that will have the least oxidization and the least remaining resin. So you find that the sweet spot. I noticed around this area it looked pretty good. And first I did some tests without any polishing just to see. So for example, I chose this 42. As you can see here, the 42, even without any polishing, was showing signs of taking up the solder, which was a good sign, right? However, the 46, which is hotter and therefore more oxidization, we saw that even though that the copper was being cleared, we found that it was beating up. And so the oxidation was at work there. And then at the other end of the scale, down at this 38, again, we saw a bit of a mixed bag where a little bit more beating, but also some good take up as well. So this all led me to looking at around about this 44%. And after polishing a bit and doing a test, I could see that the take up was much better. So it's definitely onto the right path, but it wasn't perfect. And then the ball finally dropped, the surface tension issue of having that wire brush finish and doing those tests. So I went ahead and made a PCB which was pre-polished. So before putting on the first layer of resin, I polish it to a high shine, and then I finished the PCB, cleared the pads, and then I put a bit of masking tape along one side at a 45-degree angle of the board. And then I just did a very light clean with metal polish on one half and put down the solder, and the results are really, really very clear. So the pads on the left are the ones that receive the light polish, and the ones on the right are the ones that are just straight off the CNC with no further treatment. And even on the QFN package here where I've done it on the diagonal, I didn't polish it that well in the middle, but you can see in the take up of the solder. So in the end, the problem is not that difficult. You just have to pre-polish the PCB before you coat them originally. You need to make sure that when you clear the pads, you don't burn the pads, because if you burn the pads, you're going to increase the oxidization. But you also want to make sure that you clear enough resin that you can polish off any remaining resin. That's always going to remain. It's just unavoidable as far as I can tell. So we're going to be using Pical as usual. Get my toothbrush. So you don't need that much pressure, but you do want to make sure you're pushing into all of the pad cavities, especially on that QFN package. We want to get right in those little pads. I can already see those pads are starting to shine quite well. Spin it around. I'm a little bit used to the old method where it was still quite difficult to polish these, and so I probably am overdoing it. It really doesn't require that much polishing to get rid of the residue once you've pre-polished these boards in the first place, because it just basically falls off. Amazingly, the resin is so resilient. The mask resin is so resilient, even though I'm scrubbing quite heavily in those very little sort of cavities of the QFM package. I have never knocked off. I shouldn't say that because that's what's going to happen now because I've said it. But I've never knocked off any of that mask, even with some pretty heavy scrubbing. So yeah, it just sort of tells you. Yeah, there's one thing worse than overdoing it with this, and that's underdoing it, because if you get to the point where you're assembling the PCB and the pads don't take up the solder, yeah, it's not a lot of fun, that's for sure. And back with the IPA, the last step, we want to do a couple of rounds of IPA. But the same thing, just make sure you're getting all the cavities. One more round. I should be wearing gloves, but I'm not because I'm too lazy to put them on. I'm just doing a wash over now, just to let it drain off any remaining. I'll get one clean tissue. If you have the pads popping like that, it's 100% guarantee that it will take up the solder. Now, I know there are people screaming at the screen saying, just get liquid tin. Well, liquid tin would be nice to have, and if I had it, I'd probably use it. But the first problem is that it's impossible to get in nearly all countries, and I see even in America it's even hard to get. So I don't know, this liquid tin thing seems like a bit of a fantasy, because if you can't get it, then what are you going to do anyways? And the second issue is that it doesn't address the residue issue. You need to remove the residue in any case. So I think for me, and I think for most people who are doing this process, all you need to do is you can minimize your oxidization levels just by leaving the residue on. And just before you do the soldering work, then just polish off the remaining residue and go straight to solder. So, the residue can actually, serve a purpose as well. So I think that's all fair when you take it all into account. All right, so I think we're done. I'll take some images of that. So yeah, the key word here is highly reflective, like shiny like polished gold is what you want to see. And I'm always fooling myself a little bit with this. I'm looking at it and I'm thinking, oh, it looks shiny, it looks clean. I mean, even with these, I would say they look pretty and shiny, but they're not highly reflective. And so don't fool yourself like I do. It's either right or it's wrong. It's black or white sort of situation. It's either fully polished like a mirror or it's not. Okay, so for the first part of the process will be to get the stencil and apply it. Now I've got this just mounted into a watch repair clamp, and I've got that clamped to the table so it doesn't move around. So I'm just going to remove it from here carefully. I don't know if that was carefully or not. And just double check again the stickiness. Make sure it's not too sticky. I think it'll be fine. And see if I can line this up while showing you at the same time. And this is really quite difficult. So maybe I'll take you off camera for a second and do it. So this is what I'm doing. I'm just putting this magnifying glass at the top and I'm shining the light from the top. The key area to focus on for this specific one is the QFM package, to make sure all the pads are reflecting, and they are, and the rest pretty much falls into place. You don't need to do too much. And just push it down. You don't need to push it down too hard around the edges, just around where the pads are. In this specific case, I will get little glasses out and I'll check the QFM package, and if there's anything, charcoal or something that's in here, I'll just use this pin to knock it out. So I'm going to use 138 degrees solder paste this time. I think it's just 35 grams, even though it seems to have quite a lot in here. Some people buy it off AliExpress and the photos they have showing you like this much in it, which is a joke. But this one is pretty good, this conduction. And this 138 degree one is pretty easy to deal with and leaves a relative nice result, which is also pretty nice to clean up. I'm just going to press it into that QFM package a little bit. It's really difficult. Well, this 138 actually is flowing a little bit. And one of the reasons that I sort of recommend this tube is because I found that this one, which I've opened, it's got like a seal on top of it. But once you open it, it's open, and it seems that the flux sort of evaporates a bit and it gets a bit dry. It doesn't flow as well, I think, anyway, or maybe that was the original mix. But regardless, this in the syringe seems to really maintain its state. It seems to be pretty stable and flows really well. So you really want to push it into those holes as hard as you can, especially that QFN package. I always have a lot of trouble getting good coverage in the QFN tracks, just because the stencil is just not that clean. I actually would prefer to be using a different type of material for the stencil. Obviously, I can't cut stainless steel, which they're normally made out of. I think the thickness of this stencil is possibly a little under thickness. Not really sure, to be honest, but it seems to work pretty well now that I've got those pads polished properly. If you've got too much solder, it's going to really make your components float a bit too, especially with LEDs. That's problematic. Peeling it off is a bit tricky, so if I peel off like this, then I'm going to actually pull up the resin for the QFN pads, or alternatively from this side I'll pull it from there. So I want to probably pull diagonally to try to do it, and I want to have a shallow lift. If I pull it too vertically, it's probably going to lift the paste out with the stencil. Just do it slowly, just keep lifting. And now we're pretty clear. And the rest doesn't matter, just be careful not to tear up the resin. And you can see that the stencil looks like it's lasted in pretty good shape. So we'll try to get some photos here. So you can see that the QFN package is a bit sketchy as far as the way that it's laid down. It's not neat, it's not perfect on every pad. Don't think that's a big problem, because the surface tension is going to pull it all together anyway in the right way. I think it's more of an issue of adequate volume and coverage, and I think we've got pretty good coverage there, right? I think you would agree with that. Okay, so it's looking good. So next up we're going to place all the components. So I'll just get the components ready and I'll bring you back. Alright, so here we go. So I'm just going to place them on roughly for now, and then I'm going to get those little glasses and nudge them into their final position, which I will do off camera. Alright, it looks like everything's there. I will use my watch repair glasses now and check it in detail to make sure everything's in perfect position, and, you know, a bit of treatment for my OCD. It's not really a treatment, is it? It's more of a symptom anyway. And obviously I'm going to take some photos here and give you a look at what it looks like, so you can sort of see where we're at before we actually go into soldering this thing. Alright, so I've got my hot plate up here to around about 120 degrees, so we're going to do a bit of a preheat on this. So apparently we're meant to wait for around about 2 minutes. So this is meant to be preheating the components so everything gets up to the same sort of temperature, so that when we go for the main heat, it should evenly sort of solder everything. In theory, that's the way it's meant to work, apparently. Alright, now we'll go for the 150 degrees or something like that. And there it starts to go molten. It all happens pretty consistently. Now I haven't used any glue on these LEDs to get them to sit down, so just going to go with it. Hopefully it's going to be good enough. They might float a little bit. So let's take a bit of a look at it as it is, to get a bit of an idea what the solder looks like before we clean it. So there doesn't appear to be too much residue from this solder, and that's the good thing about 138 degree solder. It does seem to consolidate pretty well. There's a little bit here on this side, but it's not too bad. I think it'll scrub off. So, more IPA. And you want to scrub pretty hard with this stuff because those little balls are really tough to get off. Around the edges of that QFM package, which I might have to touch up with a soldering iron if need be. Go one more round. Just take a look at it. Looks like I might have got lucky with a QFN, or is that one pin there? It seems like it's cleaned up alright. I don't see any garbage and things seem to be soldered pretty good, so I think it's a success. Yeah, so the QFN's a bit not perfect, so I'm just gonna hit it with a soldering iron around the outside just to clean it up. So I finished touching that up with the iron, and it's pretty easy to touch up. You just literally just rolling the soldering iron along the edges, and it just sort of balances out the solder across all of the various pins. Unfortunately, on this side I have this capacitor here, and that makes it quite difficult to get in there and access. It gets in the way, so I ended up having to remove that. Doesn't look like I put it back on quite straight, but I don't care. But it seems like there's nothing wrong with the pads. It's more of an issue of positioning, possibly solder paste consistency and solder paste volume. Anyway, I'll do some photos for you again just to show you the end result. Hopefully I can get some good shots. So you can see the QFM package is shifted slightly a little bit off center of its pads, but you know, I think it's not a big issue to have them about that far off. I think it's within tolerance and they're soldering quite well there. So these round boards are a little bit more difficult to snap out. You don't want to put any stress on the board if you can avoid it, just on the bit you want to snap off. You can see here how on the polished surface it will have a tendency to come off easier. So, but in this area here it's not going to come off ever, I think, under normal use. Yeah, it's definitely more difficult to do on these round boards. The square boards you can sort of do one side at a time, but there is no one side at a time with this. We're just about there. Alright. So I wonder how far deep we managed to cut that. And I wonder how aligned the laser was when it flipped sides. This is a good way as any to get the pin headers sort of lined up. Put in a bit of proto or breadboard or whatever you want to call this. Right, all done. Give it one last clean. Just get rid of that last bit of flux we stuck on there and Try to clean off some of these edges from all that charcoal. Where are my gloves? All right, well, there it is. What do you say, folks? Looks okay? The back side. And I actually made one a little earlier from one of the test boards that I was making to check the pad clearing process. This is it here, and I didn't put a silkscreen on it. I think it looks pretty nice without the silkscreen too, right? I think that's definitely another way to do it. I know a lot of the Apple products have given up on the silkscreen. So, yeah, you can save you a bit of time with that as well. And it still looks pretty nice. But, you know, there are a lot of things where you really want to have the identifiers on there where you can figure stuff out. So, if you want the silkscreen, you can do that too, and it comes up really nice, right? Now, what I've programmed in here is extremely basic. I'll let you know in advance. I just wanted to test if the LEDs work. I have a lot more ideas where I have like using a PCM to fade the control of the light level of each of the LEDs and doing some more interesting patterns and things like that. And obviously, I have the idea of using the I2C bus to remotely control what patterns or what degree of LEDs are presented or whatever, some sort of remote control or maybe even remote pattern programming over I2C is sort of the idea that I had. Anyway, let's plug it in and have a look at the little test program that I have got loaded. It's exciting as hell. Oh. Very pretty, isn't it? So this code is really just straightforward. It's just turning the ports on and off directly and having little delays to create this pattern and maybe some basic loops. So very, very simple. But even though it's very simple, you can still get a pretty effective result, right? And this other one here, let's plug it in and have a look at that one. It's got the same code in it. We'll run them side by side. So this one has orange LEDs, and you can see it's a lot dimmer actually, even though it's running at a higher current. So yeah, the orange LEDs are not as bright as the green ones, that's for sure. That's just the way it is. So pretty cool, right? I like it. I think it's impressive. And other than having to retouch up those pads on the QFM package, which I think that's fair enough given what we're trying to do here. Everything worked perfectly. I didn't have to touch anything else. Yeah, spot on first try. So there you go. Tell me what you think in the comments, huh? While we're just looking at this board. This is a professionally manufactured PCB with the silkscreen on it. And this is the PCB that I made with the silkscreen on it. Huh? What do you reckon? Not too bad, eh? Okay, now finally double-sided PCBs. Now originally I had planned a longer segment for this, but it looks like this video is edging up on around about 3 hours, so I'm going to try and keep it super short. Firstly, all the methods you need to make a double-sided PCB are already shown in this video, with the exception of making vias or plated holes. But if you really need through-hole plating, then you can either use rivets or electroplating. Other people have made videos on those topics on YouTube already, so you can go and search for that as need be. I've also been thinking about a better via and through-hole solution, but I don't have anything useful to share at this time, so I guess that's going to have to wait for another day. And in a prior video, I think I've already mentioned it, that for most PCBs you make, you probably can get away with just using a single-sided PCB. It's just not going to make sense to make a double-sided PCB, given that you're getting really high resolution with this process that I've demonstrated here. In any case, let me give you the basics on how to adapt my method so you can make double-sided PCBs if you want to. First, here are the files that you will typically need to process a single-sided PCB. Pause the video to see it in detail. And here are the files that you'll need for a double-sided PCB. Hopefully you should know enough about the method and FlatCAM at this point to be able to prepare the necessary files. So once you've got those files prepped, this is the procedure that you need to follow. First you need to UV resin coat both sides of the board as per step 1. Of course, coat one side of the board at a time. Next you need to do steps 2 through 10, but skipping step 9. This is going to basically complete the front of the PCB, but you're not going to be drilling those PCB through holes at this point. Then we combine steps 11 and step 2 so that we flip the PCB and align the PCB, but also install a new set of locating guides for doing the backside work. After that, we can repeat steps 4 through 9, but skipping step 8, and that will allow us to complete the backside of the PCB, and it's at this point that we actually drill the PCB through holes from the backside of the PCB. One thing to note here, however, is that when you're actually etching the backside of the PCB, make sure that you put some tape or some adhesive plastic sheet on the front side of the PCB to protect it from etching where you've actually already cleared those pads. After that, you can complete the PCB with the typical steps 13 through 17. Unfortunately, I don't see how you could use any solder paste to add any SMD components to the backside of the PCB, so you're going to have to hand solder any such components should they exist in your design. Anyway, that's it. That's going to get you a double-sided PCB. Actually, I haven't even made a double-sided PCB yet using these improved methods, but I did actually make one earlier in the development process. I think you might have seen that video. Even so, I expect this method is going to make a pretty spectacular double-sided PCB, so I'm looking forward to making one when the situation demands it. So that's it. That's everything. With any luck, I haven't left anything that's important out. Let me know if something seems to be missing or doesn't make sense. I will definitely add any fixes to a pinned comment as need be. Anyway, can't wait to see what people make with this new method. And if you do make something, be sure to let me know in the comments. So I hope everyone has a nice winter or summer as we head into the change of the seasons. I guess that doesn't work if you live somewhere like Indonesia, Singapore, or northern Brazil, but my best regards all the same. Probably got a programming video or a CNC update video up next. We'll see how it all goes. But whatever it might be, I do hope to see you then. Oh, and I just forgot. I will add the information on the detailed procedure in the description of this video. So be sure to check it out. Alright, I'll see you in the next one.